session this morning with a slight reordering of the talks. So we'll actually first have Lara speak, then, depending on whether Dave is here, Dave, and then just shifting everything up. So then it'll be Lara, then Jim, Irene, and then there'll be a coffee break. So our first speaker is Lara Anderson, and she'll be talking about Calabi-Yau fibrations, finiteness, and string dualities.
Thank you very much. I'd like to thank the organizers for what has been an excellent week. This being the last day of the conference, I have found the talks really great so far, and I congratulate them on an excellent meeting organized and a successful, hopefully, end to it. I should apologize for people expecting the review talk first. This will not be a review talk, but you can view this as sort of the theatrical trailer for what is to come. So I'd like to begin by saying that the work I'm going to talk about has spanned a few years, and this is done in collaboration with James Gray, who's also at Virginia Tech, our postdocs at the time, Xin Gao and Sungju Li, and a student, Brian Hammock. So I should say this day is going to mark kind of a departure from the rest of the week. We've heard a lot of string theory and field theory, not a lot of geometry, which is what I'm going to be talking about. And you may say, why would we be interested in geometry? Why do we, we're interested in string theory, we're interested in field theory. Within the subject of string compactifications, though, in dimensionally reducing higher dimensional string theories down to lower dimensional effective theories, of course, the question of which possible effective theories can arise in string theory is intimately linked to the question of which geometric backgrounds we can use in a string compactification. So the question, which geometry, we would very much like to answer. What are the consistent backgrounds for string theory? Can they be classified? Are they finite? What are their properties? And can we say something in general about the types of effective theories that can arise in string compactifications? So this is a very broad question. I'm going to begin with just a piece of the sort of simplest arena in which you could ask this question, which is the case of Calabi-Yau manifolds. These are, of course, not the only consistent backgrounds for string compactifications, but the easiest and the most well-studied. Even in this case, there are many open questions. So even within the class of Calabi-Yau compactifications for complex n-folds, the number of such non-diffeomorphic geometries is unclassified for n greater than 2. So we don't even know, for example, if there are a finite number of Calabi-Yau 3-folds. An even weaker question, we don't know whether the topological numbers that characterize those manifolds and appear in the effective theory. So for example, Hodge numbers, which can count the number of massless singlets that appear in effective theories, we don't know whether those numbers can also be bounded. So in this talk, I'm going to outline one approach to these rather ambitious questions, and that is trying to attack this via substructures in the Calabi-Yaus themselves, Calabi-Yau fibrations. So hopefully the notion of a fibration is familiar to most people, but a quick reminder if it isn't. A fibration is a surjective morphism from one manifold, the one we're interested in is the Calabi-Yau here, to another, the so-called base, such that for almost all points in that base, the inverse image of this projection map is homotopic, i.e. the manifold can be decomposed into a base and a fiber, a horizontal and vertical component. If you, in addition, have a continuous mapping from that base back to the manifold, such that this property holds, then this is a section to the fibration. So two quick definitions. Okay, so why do I care about Calabi-Yau fibrations? Why is this interesting? Well, for starters, fibrations play a very key role in string dualities. So basically, any duality you can think of, there's a fibration in play. For example, heterotic F-theory duality is based around elliptic and K3 fibrations in the compactification geometries of the two theories. Heterotic type 2A, F-theory, M-theory duality with elliptic fibers, or more generally circle fibers. In addition, the fiber-based decomposition that I described, so having this additional substructure in the manifold, this actually simplifies our analysis of the geometry in the process of doing a string compactification significantly. For example, it changes the form of topological numbers, such as the intersection numbers of the manifold. You can work out nice properties of those. Even the form of the metric can decompose nicely in terms of the fiber and the base. But here's the real reason that I want to talk about fibrations today. There is a theorem due to Mark Gross and based on previous work by Antonella Grassi that's 25 years old, which says that the set of genus 1-fibered Calabi-Yau 3-folds is finite. A bit of terminology, I'm going to interchangeably use the word perhaps torus-fibered, genus 1-fibered, or elliptically fibered. All of those represent a fibration in which the fiber is a one complex dimensional manifold with C1 equals 0, i.e. a Calabi-Yau one-dimensional fiber. In general, if a section exists, we refer to it as an elliptic fibration because there's a marked point. If not, we'll say genus 1. So in general, torus-fibered Calabi-Yau manifolds are known to be finite. That's an interesting thing. So within Calabi-Yaus, we know that there's at least a subset that can be bounded. This has recently been explored for higher dimensional Calabi-Yaus, not just threefolds, by Dicerbo and Sfaldi, starting in 2016 and with ongoing work. They attempted to extend Gross's theorem to Calabi-Yau 4 and 5 folds, and so far they have an important piece of this, which is that there's a finite number of base manifolds for elliptically fibered 4 and 5 folds. Okay, so you may still be saying, why are we going here? Why is this interesting? It's nice that there's a finite set, but what is that going to tell me about the broad questions that I outlined before? So here's the idea. First, a few results on fibrations that are going to be important to us. For Calabi-Yau n folds, they can only be fibered by m folds with C1 equals 0, i.e. Calabi-Yau or a billion surface fibrations, where the dimension of the fiber is strictly less than the dimension of the manifold. So for example, a Calabi-Yau threefold can only admit fibers that are Calabi-Yau 1 and 2 folds as fibers, so a torus fibration or a K3 fibration. And importantly, for what I'm about to say, the existence of such a fibration is a deformation invariant statement for n folds with n greater than 2. So not K3, but everything bigger. If you have a fibration, that's something that you can't lose at any deformation of the manifold. It's a topological invariant to state. So here's the idea behind Gross's theorem, and this is what I really want to talk to you about today. We know that elliptic or genus 1 fibered Calabi-Yaus are finite. If you could understand, and this was actually the motivation that Gross himself stated in his theorem 25 years ago, if you could understand this Venn diagram, you could understand where elliptic Calabi-Yaus fit within the set of all Calabi-Yaus, then you might have a shot at trying to understand whether all Calabi-Yaus were finite, whether they could be classified. So what would that look like? Imagine that you start within the finite set that you could enumerate carefully and bound. If you could understand how to deform away from that in this broader moduli space, how to wiggle outside the smaller circle, then you could perhaps classify everything. So what would it mean to wiggle outside that circle? What that means within the space of compactification manifolds is that we want to do geometric transitions which can deform the topology of that manifold. So here's an illustration of the famous conifold type transition. That's one example. Of course, Miles-Reed's conjecture is that all Calabi-Yaus could be related by geometric transitions of this type. So if you could actually characterize or classify the geometric transitions that could get you out of this circle into this one, in principle, you could have a shot at trying to bound and characterize all Calabi-Yaus. So the goal of today's talk is trying to tell you a little bit about where this subset fits inside the bigger one. So let's try and observe what we know about fibered Calabi-Yaus so far, and then what would we hope to understand. So let's look at the data set of Calabi-Yaus that we know about so far. What we've characterized so far in the last 20-odd years of trying to look at Calabi-Yaus and build them is we have a data set of around 1 billion manifolds. This is primarily consisting of the toric hypersurface data set constructed by Kreutzer and Skraka in 2000. Another consistent data set, the very first one that was written down in a phenomenal feat of 1980s computing done at CERN on magnetic tape, I should say, was the complete intersections in products of projective space, the so-called CCs. This was done in 87. So we have consistent data sets of manifolds, about 1 billion to play with. So now let's look at those billions of manifolds that we have. Let's throw a dart somewhere in the middle and say, what do we observe about that data set? So the first immediate observation that we can make is that if you throw a dart anywhere in the data set of 1 billion manifolds we know, you are going to hit a fibration. This is not a rigorous statement so far. This is very vague. I'll start making this rigorous in a second. So it appears from very naive observations of the data set that we know so far that almost all known Calabi-Yau 3 and full folds appear to be fibered with every possible fibration that their dimensionality allows, i.e., if they're a threefold, they appear to generically all be elliptic and K3 fibered. For Calabi-Yau 4 folds, they can admit Calabi-Yau 3-fold fibrations, etc. The next observation that you make, if you pick a random manifold out of the hat, is that these generic manifolds do not admit just one elliptic fibration, they admit many, orders tens, hundreds, perhaps thousands of different fibrations for one manifold. That's different ways of describing the manifold, cutting it into a fiber and a base to describe the total space. So those are two strong claims and kind of vague statements. So let me try and make this more precise and explain how one goes about actually studying this and understanding what we see so far. So here is a plot of the known Hodge numbers from the Kreutzer-Skarka dataset of toric hypersurfaces. The axes here are the sum and difference of the Hodge numbers H11 and H21. And various people, in increasing interest and intensity recently, have been looking at whether these manifolds are fibered or not. So these set of authors, I'm going to particularly highlight the work of Waddy Taylor and his student Yuchen Huang, which some of which appeared just recently and more is to appear. Various people have been studying how generic fibrations are within this data set. And this was the only plot I could find from several years ago. This is from Waddy's paper from 2012. You can plot the known Hodge numbers of elliptically fibered manifolds over the Kreutzer-Skarka data set. This is much more dense now, I should say, compared to 2012. But you can see that generically, this appears to be these Hodge numbers are populated by elliptically fibered manifolds. In addition, the extremal manifolds in this data set, going all the way up to the highest known Hodge numbers, all of these are elliptically fibered. These bounds on elliptically fibered manifolds are very well understood, and it appears that they're quite generic within that data set. More precisely, what I want to tell you about today is a simpler data set where you can make this very exhaustive. So I want to begin with the 7,890 complete intersection manifolds that can be defined in ordinary products of projective space. And this is what my collaborators and I attempted to enumerate precisely. So for the CC3 folds, the claim is that 99.3 of them admit an elliptic fibration. And for CC4 folds, of which there are about 900,000, these people, Gray, Haupt, and Lucas, in 2014, also enumerated fibrations. They found that 99.9 of those were fibered as well. So what are these matrices that I've drawn here? These are matrices, so-called configuration matrices, which denote the degree of a manifold that is defined as an algebraic complete intersection in a given ambient space. So the left-hand column here, P2, P1, P2, this represents a product of simple projective spaces. And then these columns represent the degrees, multi-degrees, of equations within that space. So this is the complete intersection of two algebraic equations, one of which has degree 0 in these coordinates, 1 in this one, degree 3 in this one, and 310 in this one. The superscripts here are the Hodge numbers, H11 and H21. So what I've denoted here in blue and in red is that when you have an algebraic description like this, it's very easy in some circumstances to spot a fibration. So notice in this manifold, if I were to plug in a solution to this first column equation, if I were to choose a solution to the points that satisfy this 1,3 equation, that would give me fix a point in this two-dimensional base surface. If I then plug that into the remaining equation, that gives me a cubic in P2. That is a elliptic curve, excuse me, not elliptic curve, a genus 1 curve, that is a torus. And so over every point in this red hypersurface in this base manifold, I'm going to end up with a torus above it, i.e. I can see just from the algebraic form of this manifold that it is fibered. That was a little bit fast. If you haven't played with these configurations before, this may not be totally easy to see. But if you just write out these equations, it's easy by inspection to see that the algebraic form of the manifold guarantees a fibration exists. Okay, you can play this game for bigger manifolds. So notice this is a fibration within a threefold, as I've defined it here. Down here, I've written down a configuration matrix describing a Calabi-Yau fourfold. And you can spot different fibrations using different subsets of the matrix. So here, what I've highlighted in blue, these polynomial degrees represent a elliptic fibration over P1 times P1 times P1. If I add in the red row, this gives me a K3 fibration over P1, P1. If I add in the green, this is a Calabi-Yau threefold fibration over P1. So you can parse out sub-fibrations. This is a fourfold that's fibered by a threefold, which in turn is fibered by a K3, which in turn is fibered by an elliptic curve. So this is like Russian dolls. The manifolds are nested inside each other. The fibration structure is ubiquitous as I move down. Okay, these are simple algebraic descriptions of fibrations that I can just spot with very minimal effort. And these numbers here, 99.9, 99.3, this is what you do if you teach a computer to go through the algebraic descriptions of the data sets and just count how many of these can you find. It's a non-trivial programming problem, but you can do it quite readily. And you can count how many obvious elliptic fibrations you find. Perhaps a little bit more surprising than just being able to find elliptic fibrations is that when such manifolds have fibrations, they generically do not have just one. In fact, there can be many. Let me illustrate that again with one of these simple complete intersections. Here I've written the same manifold twice, and I've used symmetries in the definition of this manifold. So what do I mean by that? Here, the product of projective spaces that I write down, there's no preferred ordering, so I can switch rows in this configuration matrix any way I like. Likewise, the columns represent degrees of equations that I'm imposing, and there's no order to those degrees, so I can interchange columns as I like as well. So if I play this game of trying to observe fiber and base decompositions in these degrees, it's very readily clear that just by permuting the rows and columns of this matrix, I can pull out here an elliptic fibration given by the blue degrees over this surface, which is actually a dp2, I believe, and another elliptic fibration over p1, p1. So I can decompose the same configuration matrix in two different ways to immediately spot two different fibrations. Again, these are just obvious fibrations from the elliptic, from the algebraic description of that manifold. So you can do that for the data sets as well, and this was done for 4-folds and by my collaborators and I for the CC3 folds. And what's plotted here is the abundance, the number of times that a given number of fibrations appears in the data set. So as you can see for the 4-folds, sort of in the middle here, about 50 different fibrations for a 4-fold appears to be the peak of this one. But if you go out, in fact, in some manifolds, up to 350 different obvious fibrations, these are all genus 1 fibrations, are appearing for one manifold. Likewise, you can do the same for the CC3 folds. And you can see that for 3-folds, again, somewhere in the tens is where this is peaking. And out into the hundreds, there are manifolds that emit hundreds of different fibrations. OK, so the first first pass at this for one data set, you start looking at them. Basically, all of them appear to be fiber. So the first thing we did, we scanned for obvious fibrations in the CC3-fold data set. Again, this is about 8,000 manifolds, and we find 139,597 genus 1 fibrations in this obvious algebraic way. About 30,000 K3 fibrations and 208 nested combinations. Those are different ways that you could link the K3 fiber and the elliptic fiber. However, there's no guarantee that these obvious elliptic fibrations are the whole story. We need to be able to characterize fibrations independent of an algebraic description of the manifold. And fortunately, there is the mathematical technology to do so. So it is possible to systematically and completely characterize elliptic fibrations. I'm being a little sloppy here in saying elliptic and genus 1 interchangeably. Forgive me for that. Genus 1 fibrations by characterizing the base. So there's a conjecture due to Kolar, which is based for 3-folds on a proof due to Wilson and Ogiso, that says that basically if you can control certain divisors inside the manifold that obey intersection properties, namely that they intersect positively with all curves, if you take the maximal intersection number of that divisor with itself, you get 0. If you take the dimension -1, you get something non-zero. If a divisor exists with these properties, then a fibration exists. In the interest of time, I'm not going to motivate for you quite why this works. It's a cool story, and you can ask me over coffee if you're interested. But the punchline here is that it is possible, independent of an algebraic construction, to actually characterize all fibrations of a manifold and to see how many manifolds, again, admit fibrations. So we want to know, can we enumerate all the following? To do that, in order to satisfy the criteria I just wrote down, you need explicit control of all divisors. You need to understand the Kähler and Morrison cones of the manifold and the intersection numbers. This is actually really hard for any data set, and in our search for these fibrations, enumerating this data carefully for all the manifolds in the set was the hardest part. I could give an entire talk about how we did that, but again, I'm not going to bore you with that right now. What I want to say is we did this, we got this to work, so what we want to see is how does an obvious fibration count compare to an exhaustive fibration count, and we developed the tools to do that. So the result, we scanned over the same data set of 8,000 manifolds to start. What we find is that when you have manifolds in which the Kähler cones strictly descend from the ambient product of projective spaces, the obvious fibrations that you would write down algebraically appear to be everything. Otherwise, you can find many more. So the statement is that 99.4% of all these manifolds are genus 1 fibered. And here's the interesting one. You might be saying, OK, but what good does it do me that they're almost all fibered? That's interesting, but so what? The interesting thing here is that they are all fibered as H11 increases. And this has been also shown by work by Wadi and his collaborators. Within the known data sets of Calabi-Yau's, as you increase H11, it appears that everything admits a fibration. For this particular data set, for everything beyond H11 equals 4, they are fibered. So we all know that the quintic, the simplest Calabi-Yau we could write down, that's H11 equals 1. That guy does not admit a fibration. But as you start increasing H11, as you start moving upwards in this famous plot of Hodge numbers due to Kreutzer and Skarka, it appears that you are going to find more and more fibrations, i.e. generic fibrations. We classified 377,000 fibrations for a set of 4,000 manifolds for which we had complete control of the Kähler and Moring cones. And we find many that were not obvious from the algebraic description. So for example, for one manifold which can be written as an anticanonical hypersurface and a product of two DP7s, this one manifold gave rise to 15,000 different fibrations. This is an extraordinary redundancy in description of the same manifold, only several of which were obvious, and they can be grouped formally into birational equivalents in nice structure. For one surprising manifold, we actually found a parametrically infinite set of distinct elliptic fibrations. This is a bit of a surprise. Thank you. This was studied previously in the mathematics literature. We found a new parametric description. This corresponds in any effective theory to a U-duality, a continuous U-duality group between these fibrations, which I'll talk more about in a minute. And importantly, you might say, okay, well, this is a very simple algebraic set of manifolds. How do you know that you're not just looking at a lamppost effect? These are all fibered because you built them simply. Maybe that's just how you built them. So we've tried to extend this to other known data sets. Recent GCC construction of manifolds that James and I have been working on. We also looked at manifolds that are non-simply connected because they have very different properties. And once again, we find that fibrations are ubiquitous and multiple fibrations are also the norm. So with my remaining 5 minutes, I want to say just briefly, what about the physics of this? So I clearly am interested in this in order to try and enumerate the finiteness of the Calabi-Yau data set. This also has strong implications. The fact that basically everything is fibered has strong implications for string dualities. So just as several brief examples, for example, in 6-dimensional compactifications, you can look at M-theory, F-theory relationships between 6 and 5D. If you have F-theory on a manifold that admits many, or M-theory, either one, on a manifold that admits many different elliptic fibrations, what does that mean for the F-M duality? So as an example, here's a manifold with H11 equals 7 and H21 equals 26. What you find by studying M-theory and F-theory in 5 and 6 dimensions is interesting webs of theories. In this case, is however many I have here, 9 or so theories, with entirely different spectra in F-theory. So here's the F-theory backgrounds, gauge symmetries, number of vector, tensor, and hypermultiplets in 6 dimensions, all of which share the same M-theory limit. This is of interest if you're studying string effective theories because we use a lot of times information about forms of Chern-Simons theories, forms of the effective potential from M-theory to uplift to information about F. So these are very disparate F-theory vacua, some of which contain superconformal loci, which all share a secret origin in one M-theory. Likewise, you can say something about heterotic F-theory duality. This is just a brief reminder. In order to do heterotic F-theory duality, you need elliptic fibrations on the heterotic side and K3 fibrations in F-theory. You can say, what happens if the F-theory geometry is multiply fibered? And you can run through different possibilities. This is basically the Russian doll effect again. Multiple K3 fibrations can appear in one F-theory background. This can lead to different heterotic theories that will give the same effective theory in one dimension lower. Multiple K3 fibrations with the same elliptic fibration can lead to identical heterotic effective theories on different geometries. And finally, one K3 fibration with multiple elliptic fibrations can lead to distinct heterotic theories on the same Calabi-Yau geometry. If you're like me, I get confused just even saying that, so yes, takes a minute to parse that. But basically, by playing with the Russian dolls of which fibers nest inside which other fibers, you can start to say, what will I expect from these string dualities? And the punchline is that we are able to enumerate known and new dualities this way, using what we know about fibration structures to form sort of a map of known string dualities. So simple examples, things like SO32 E8 cross E8 duality in 8 dimensions can be realized as multiple fibrations. Morrison and Vafa showed in the 90s that you could view the heterotic, strong, weak coupling or perturbative, non-perturbative duality of Duff, Manazi, and Witten as multiple fibrations in an F-theory dual. My collaborators and I have generalized the heterotic duality to higher numbers of tensors using this, using the geometry of conic bundles. So again, you can see familiar dualities and new dualities simply by inspecting multiple fibrations. One that I'm excited about and we're working on now is we want to consider novel dualities that we haven't seen before. And there's one in particular that is interesting in 4 dimensions. So in 4 dimensions, if you have a heterotic elliptically fibered geometry that is elliptically fibered in more than one way, this leads to F-theory vacua on 2 distinct Calabi-Yau fourfolds with different G-flux which magically gives the same effective physics. And as far as I know, this is a completely ununderstood or completely unknown duality in play here that these multiple fibrations are bringing to light. So understanding the physics of this is something that we're actively working on. Okay, that was a lot all at once, so let me take a step back and say, what do I hope you take away from this talk? The punchline of today's talk is that we are beginning to systematically enumerate fibrations within known Calabi-Yaos, and more importantly, we are attempting to extend those techniques of classification to Calabi-Yaos in general. We're approaching this, since we're not mathematicians, we're approaching this both geometrically and also using tools from the physical theories to try and constrain this problem. And what we are seeing is that evidence is accumulating that as H11 increases, all known Calabi-Yau manifolds appear to be elliptically fibered, generically with multiple fibrations. This is persisting in every data set that we know how to build, and we are attempting to establish this for all Calabi-Yau threefolds. If this works, this would be a proof, at least, that the topology of Calabi-Yaos is bounded, and that could have profound implications in terms of a swampland, in terms of string effective theories. This could be a very important result. I gave you a lightning tour of the fact that multiple fibrations can be used to impact a huge array of dualities and form a duality cartography. And we're trying to use this to discover new aspects of duality and also to simply and geometrically encode known ones. And I'll stop there. Thank you.
Okay. Thank you very much, Lara, for this nice talk. Are there questions? There's a question there, Massimo.
You said that there is a manifold which has an infinite number of fibrations. Can you say a few more words about that? Are there more constraints that can...
Yeah, so that seems super weird. It was weird to us too. So what happens with this manifold, geometrically, this thing has a non-simplicial Kähler cone. So it has an infinite number of fibrations, but they are all, they're sort of a infinite copy of the same physics. So this was actually first studied by Aspinwall and Gross in the 90s. So they observed that there was an infinite number of K3 fibrations in this, and they looked at heterotic F-theory duality. What they found is that you get sort of seemingly different looking heterotic duals if you use this infinite number of K3 fibrations in F-theory, but these are all related by a continuous U-duality group. So in some sense, in terms of infinite numbers of heterotic or string solutions, this is not a infinite tower that is interesting to you. This is just a very redundant description of one possible vacuum. Interestingly, though, is the fact, to me at least, that this only appears in the manifold with H11 equals 1919. This is the only Calabi-Yau that has this property. And this thing appears all over the place, and I don't really understand why that's new.
Roddy, down here, please.
Great talk, Laura. So related to the last question, when you found cases where there were multiple fibrations, did you look at the automorphism symmetry of those Calabi-Yaus and check which? And for instance, you could ask the question, if there's an automorphism symmetry of order 10 and you have 20 different fibrations, you could ask how many automorphism
So you're saying, can they be mapped into
classes.
each other?
Right.
Yeah, all of the numbers I'm giving are modded out by all automorphisms. None of these,
Okay.
so
So those are all modded out.
redundancies, if you keep automorphisms in play, these numbers would jump to billions instantly.
Great. That was
so yeah, I should have said that more clearly. We very carefully removed redundancies from everything.
Thanks.
Any more questions? I don't see any more. Let's think. Oh, there's a question. Where? Oh. I don't see. Was there a question? No? Okay. So let's thank Lara. Actually, the next talk will be Dave, just in case we arranged, but actually it will be Dave. So thank you.
Okay.
Okay, so the next speaker is Dave Morrison, and he will tell us about 3 roads to 4-dimensional supersymmetric physics.
Thanks very much. Thanks to the organizers for drawing me away from Santa Barbara to this wonderfully humid place. So I'm going to talk about 3 different ways of getting to 4-dimensional supersymmetric physics. Do we still need to get to 4-dimensional supersymmetric physics? I'm not sure. But this is one of the things that string theory is pretty good at. It has been good at for quite a while, and there's been some recent progress, so I'm going to tell you about the recent progress. The first way, the oldest way, is the compactification of the heterotic string. This was an idea from the early days of string theory that we could take one of, either of the heterotic strings, but the one that's been focused on most for phenomenological purposes is the EA cross E8 string. We could take that and compactify on a Calabi-Yau threefold. The reason that we choose Calabi-Yau threefold is thanks to Yau's proof of the Calabi conjecture, which guarantees solutions to Einstein's equation and produces, because there's a parallel spinner in the system, produces a supersymmetric vacuum automatically. But because we're using the heterotic string, which also has a gauge sector, we specify not only the manifold, but we should also specify an EA cross E8 bundle on the manifold, a bundle with that structure group. Typically, those bundles have been constructed by taking a subgroup of EA cross E8 and using a vector bundle rather than a principal G bundle, but one could, in principle, do the G bundles as well for an E8 cross E8 bundle. And in that way, produce a lot of possible 4-dimensional supersymmetric compactifications. So the mathematical ingredients are all taken from algebraic geometry, thanks to Yau's theorem. We need a Calabi-Yau threefold, and on that Calabi-Yau threefold, we need a bundle structure. We need a connection on that bundle, but there are additional results due to Donaldson, Uhlenbeck, and Yau, which relate the existence of appropriate metrics on the bundles to stability conditions about the bundles, which are also problems in algebraic geometry. So this historical fact is actually why somebody such as myself, who was originally trained in algebraic geometry, can play a little bit in this arena. The algebraic geometry turns into physics by means of compactification of the heterotic string on a Calabi-Yau threefold. Now, back in the 90s, we learned a lot about, or the 80s and 90s, I should say, we learned a lot about higher dimensional versions of string type theories, including M theory, which I'll get to in a minute, but also including F theory. So the second method that's been studied a lot for finding supersymmetric compactifications in 4 dimensions is via F theory. My current point of view on F theory is that F theory is a variant of the type 2B string in which the axiodilaton field tau is allowed to enjoy its SL2Z symmetry. So we take, as a geometric avatar of tau, we take an elliptic vibration. We want a family that's got a variable tau, but on the base of that elliptic vibration, or the parameter space for tau, we compactify the type 2B string with, again, a variable tau. And again, there's a really good way of getting down to 4-dimensional supersymmetric physics just by taking an elliptically fibered Calabi-Yau fourfold. So I want to take the base of my tau fibration to be complex dimension 3, again, to get down from 10, the natural dimension of the type 2B theory, to the 4 dimensions, 4 space-time dimensions that we see around us. Please ignore the column on the left, which was included by mistake. Has nothing to do with this talk. I just realized it's there. It is related to F-theory, however, and the F-theory compactification scheme is something that we've made a lot of progress on in the last few years. We've learned a lot about how to specify the effective gauge group and effective matter content in an F-theory compactification, although we still have some distance to go in understanding all the details of that. But we've also learned about dualities between F-theory and other theories. So Laura's talk just before mine, as it happened, indicated a lot of the indicated the ubiquity of elliptic fibrations among Calabi-Yau manifolds. She was talking more about Calabi-Yau threefolds, but for this particular purpose, one would want Calabi-Yau fourfolds instead. The third road, where there's been some rather striking progress recently, is the compactifications of M-theory on manifolds with holonomy G2. So among the solutions to the basic problem, the basic holonomy problem, when can you get a covariantly constant spinner in 4 dimensions as part of the effective theory of some compactified theory, one discovers in the list of possible mathematical special holonomy examples this case of G2 holonomy. And the problem has been that unlike the previous cases where either one wanted an one wanted a Calabi-Yau threefold with a particular bundle associated to it, that's a problem in algebraic geometry, or one wanted an elliptically fibered Calabi-Yau fourfold, that's also a problem in algebraic geometry, essentially. There has not been a good mathematical way of approaching this problem of finding the manifolds on which to compactify with holonomy G2. So it's been known for a long time that you could get interesting compactifications, interesting 4-dimensional theories out of M-theory compactified in such a manifold, but we haven't had a good supply of such manifolds. The first compact manifolds with holonomy G2 were constructed by Dominic Joyce in the mid-1990s based on orbifolds of tori and their resolutions. So he showed that there existed resolutions of toroidal orbifolds, 7-dimensional toroidal orbifolds, which had the G2 holonomy property. Subsequent to that, there was a construction by Kovalev, which was really amped up in significant ways by Corti, Haskins, Pacini, and Nordstrom in the last decade or so, in which there's another way of building manifolds with holonomy G2, which we can start to use for physics. So Jim Halverson and I, some time ago, explored the basic physics implications of that CHNP construction. What sort of 4-dimensional theories could you possibly get out of such spaces? One of the difficulties has been that the mathematicians have been shooting for actual manifolds with this holonomy, but we've known for a long time, since the 90s in fact, in physics, that we want singular spaces with this holonomy because we want the singularities to provide us with enhanced gauge symmetry and, in some cases, chiral matter for the use in these compactifications. And those problems, the problems of enhanced gauge symmetry and chiral matter, are not ones that have been directly addressed by the most recent mathematical constructions. However, I'm part of a Simon's collaboration that's working on this problem, and part of the goal of the collaboration is to tell the mathematicians what they ought to build so that we can get a good supply of G2 holonomy spaces, not just manifolds, which will have good properties with respect to the 4-dimensional supersymmetric compactifications. So if those are still things that we want, four-dimensional supersymmetric compactifications. We'll have a bunch of them, I think, in the near future due to modifications of the mathematician's construction. I do want to take a minute to describe one particular class of compactifications which I worked out in collaboration with Andreas Braun, Sakura Schaffer-Nemecki, Michele Del Zotto, and Magdalena Larfors during the past year. So we started with a particular class of G2 compactifications, which we built out of Calabi-Yaos in some particular form. And the compactifications we had the property that they could actually be realized in any of these three roads. The same physics could be described by compactifying on a manifold with G2 holonomy, or compactifying in F-theory, or doing a heterotic compactification. And the interplay between those three aspects allowed us, in that particular case, to explore a lot of the connections between the details of the four-dimensional physics that you get out of those compactifications. So I commend that paper to your reading if you're interested in what we've been up to. I should say that the recent progress in a lot of the recent progress in heterotic compactifications has been more or less along the lines that Laura was outlining, namely detailed explorations of the vast existing body of Calabi-Yau manifolds, and trying to understand what you can extract from the knowledge of a lot of possible ways of doing these compactifications. In F-theory, the recent progress, as I've mentioned once before, has been in understanding some of the details of what you get out of an F-theory compactification. And for this purpose, I really recommend Timo Vigant's recent TASI notes on F-theory, which have a lot of the details. And in this G2 compactification story, things are still emerging. And there, as I've mentioned, have been some, there was a recent project that I was involved with that explored the G2 compactification in some detail. So I had more slides. I don't know what happened. Only 5 slides. Okay. So okay. I think the best thing to do is just to keep talking in the talk, since I do have a little bit of time left. But maybe I will consult what I thought I had on my slide. Well, sorry. Maybe the best thing to do is to keep talking. So what? Yeah, as I said, we can use a blackboard. So so this basic new construction of G2 compactifications works by sewing together. Is not readable. Okay. I should write bigger. Okay. All right. Okay. Okay. I have a couple of pieces, and in these pieces I have an asymptotic structure. And the asymptotic structure is essentially that of a K3 surface crossed an S1 across a radial direction R, going toward the boundary of the manifold. And I have 2 of these things, and I glue them together. This is the basic so-called twisted connected sum TCS construction, which is the new construction that's available. And I emphasized in some sense at the beginning of the talk that I was able to play in this playground somewhat because it was algebraic geometry. Well, these two asymptotic pieces that one uses to glue together to this twisted connected subconstruction are actually K3 fibered phono threefolds, and the K3 fibration structure is what you're seeing toward the end of the phono threefold. So you're picking out one particular K3 surface, and then you're gluing them together in a way that preserves the G2 holonomy of the ambient space. So the way that we're hoping to extend constructions like this is to allow the K3 surfaces to have some singularities to begin with, which would propagate through the entire gluing process and would give us a natural source of gauge fields in the compactified space. We are still figuring out how to engineer the corresponding singularities that would give chiral matter in the four-dimensional compactification. Wow, that's interesting. Good job, guys. Okay, maybe that's enough to say about the new constructions for G2 manifolds. These two basic building blocks, as I mentioned, are phono threefolds. So phono threefolds are something like Calabi-Yao's, but they have minus kx is effective, and the K3 surface in question is minus kx for the phono threefold. So I take a particular K3 surface, which is an anticanonical divisor in this phono threefold. I remove another K3 surface, which is an anticanonical divisor on that threefold. I look at the structure, the holonomy structure, which they have, and I have to perform a particular change of complex structure from one K3 surface to the other before doing the gluing, and then I can do the gluing of the things together. So the summary is, I didn't make a summary slide, but I should have. The summary is that this new construction has provided us with a great new place to make calculations and explicit explorations of four-dimensional supersymmetric vacua. We've started to do that in a systematic way. And as I mentioned, we've found one example of this construction, which has representatives in each of the three different duality frames for getting to a four-dimensional supersymmetric compactification. And we plan to continue this line of approach for some time to come. Maybe I'll stop there for questions.
Okay, so we have a lot of time for questions. Herman.
Sorry.
I think we can maybe have sort of a discussion for at least some time.
Well, I have what can you say a few words about the status of non-supersymmetric compactifications? And the question is, what if nature decides or refuses to be supersymmetric?
Yeah, what if nature refuses to be supersymmetric? That's a really good question. That's why, in a way, at the beginning, I was asking, is it still interesting to construct supersymmetric compactification? What we're doing at the moment is sort of still exploiting the mathematical structure of supersymmetry, which we would find in four dimensions. I don't think supersymmetry is completely ruled out yet in Switzerland, but I think it's getting close. I think some other explanation for example, the hierarchy problem is going to have to be found. And if that's found, there will be a question that arises: can we make ultraviolet good ultraviolet models of four-dimensional physics which don't involve supersymmetry in four dimensions? So I don't have direct ways of saying in this program how to get non-supersymmetric models. One can ask whether breaking a supersymmetric model was necessarily the best way to get to non-supersymmetric model, maybe we'll have to go back to a different kind of high-energy model for physics. It's a good question.
Any other questions?
I mean, I'll just comment that the split supersymmetry and many variations where supersymmetry is broken between 30 and 100 PeV is still very well motivated. I would say that at this point is the leading candidate.
Okay.
I just also make a quick comment related to this question of supersymmetry versus non-supersymmetry. I mean, one of the things that Nadi said in the first day of the meeting was that one of the striking things we're learning in field theory is that things which we learned about through the power of supersymmetry, which we might have thought like dualities are somehow special to supersymmetry, some of those are still characteristic features of non-supersymmetric field theories. And so in many ways, using supersymmetry to understand compactifications down to 6 or 4 dimensions is a way of getting a controlled family of string compactifications where we can observe various phenomena. And it may well be that some of those persist in the non-supersymmetric theories. So for instance, from the F-theory point of view, and I think you guys are now seeing this from G2 as well, and we know from heterotic that typical vacua have these multiple non-abelian gauge groups that you just can't get rid of. We know that's true in 6D with one supersymmetry. It's still true in 4D with one supersymmetry. One might hope that something like that is still going to be a lesson that we can take over to non-supersymmetric string vacua. There are, somehow E8 and G2 are going to play an important role even in non-supersymmetric string vacua. So I think we can learn lessons that may still be relevant even if SUSY is broken at the Planck scale.
Eva?
Since we have time, let me also comment on this point. So,
Sure.
I mean, I agree with what has been said, except for the idea that the prejudice should be that it's a small deformation from supersymmetry. I think the exploration of the supersymmetric case for its own sake is very interesting. But when it comes to control, much like in the standard model of particle physics and what we know about cosmology, perturbation theory is sufficient. So what supersymmetry buys us most, in my view, is the ability to extrapolate to strong coupling in appropriate circumstances. That is a wonderful tool that we have, and it's led to things like black hole entropy counts and the supersymmetric duality web. But there is no non-circular argument that I've heard, against the perturbative analysis of what seem to be the much more generic, higher scale supersymmetry breaking models in string theory. Also, just as a slight aside, but sort of on this topic, if we believe that QCD is a string theory, that has no supersymmetry at any scale. So, the idea that, thou shalt start from supersymmetry, I think, I don't find those arguments satisfactory.
Please.
Can respond. Sure.
I liked what she said.
So I just have a comment on the G2 manifolds.
Yeah.
Unfortunately, it takes a relatively complicated nested set of singularities to get something similar to real physics.
Right.
So it'll probably be a multi-step process to go from smooth G2 manifolds to semi-realistic models.
Right. So getting the gauge group is the first step, and that's what I started to indicate on my slide, my blackboard there, that if I manage to take my K3 fibration, having singularities, that I can engineer the gauge group. But I completely agree that the kind of isolated singularity, the codimension three singularities which led to chiral matter in that old work that you did with Acharya and other work from that same era, that's going to be challenging.
Maybe I can make a comment about this. So in this case, in the TCS constructions, they always will have codimension 6 singularities. So you actually never get chiral matter. But maybe through these dualities, so Dave hinted at it, that there are dualities between TCS G2s to heterotic on the Schön that Lara talked about, the 1919 H11, H12 Calabi-Yau, and then also to the F theory on the Donagi-Grassi-Witten Calabi-Yau fourfold So each one of these steps doesn't actually generate any chirality. But you could modify the Schoen manifold, possibly, and then try to track what that corresponds in the TCS. That would be one strategy. But in these geometries, you will never actually get an interesting color spectrum. Yes, Leonardo, back there, please.
Thank you. Since we have more than half an hour left, I was wondering if you could give us a brief presentation of some other aspects of recent developments. So you have emphasized so far applications to string phenomenology.
Right.
There are, of course, very interesting applications of compactifications to non-perturbative phenomena in quantum field theory or dimensional superconformal field theories. You had a recent paper with Brown et al. About getting non-perturbative superpotentials in N=1 theories by G2 compactifications of M theory. Perhaps you could give us a brief presentation about
that. Sure, perhaps I could. There's I can't find the file that I thought of.
Okay, well, do you want to say something about it?
I'll try to say something about
Okay.
it. In fact, these high-dimensional theories have also been used to produce interesting conformal field theories in various dimensions. So I wasn't really, I wasn't planning to talk about that part so much, but since you've prompted me, I will attempt to do so in a less than well-prepared way. For example, if you start with the F-theory constructions based on Calabi-Yau three-folds instead of Calabi-Yau four-folds, you naturally produce six-dimensional physics instead of four-dimensional physics. And with various collaborators, all groups of which involved VAFA, we did some classification of 60 conformal field theories based on an F-theory construction. So the basic idea of that classification was that in order to get a conformally invariant theory in 6 dimensions, you would need something to shrink in the base of the K3 fibration. And if something shrank in the base of the K3 fibration, namely a curve or a collection of curves, you could engineer a 6-dimensional conformal field theory in that way. So we have a complete classification of all the 6-dimensional conformal field theories that can be engineered in that way, modulo one caveat, which is that there is a slight variation of F-theory involving so-called frozen 7 branes, and that's an aspect of F-theory which wasn't explored too much in recent times until a paper a few weeks ago. And in that paper a few weeks ago, we did not finish the classification, although we pointed to other other examples of the class in the classification. We did not complete the classification, so that's still to come, a completion of the 60 classification. One can then go from 6D to 4D and try to engineer 4-dimensional conformal field theories in a similar vein. The ultimate origin of those 4-dimensional theories will be, again, the F-theory construction. So again, I'm somehow on F-theory instead of G2 at the moment. One could also try to directly get to 4-dimensional conformal theories using G2 constructions, and that would involve something shrinking in the base of a G2 manifold. That has not been explored very systematically yet. So the route that we have to 40 compactifications is via 60 compactifications at the moment, and we have a pretty good handle on all the 60 compactifications. That's covered, I think, someplace else in this conference by somebody.
So in view of the fact that we entered into this discussion section, it might be better to do that at the this panel discussion we're planning at the end of this conference. So I suggest that we'll shift the entire program for half an hour until the 50th anniversary session, so that the 50th anniversary session will have 2 hours rather than 90 minutes. So let's thank Dave.
Okay.
I have one announcement to make. I was told that we discovered a passport and boarding pass of a certain person. That person has received an email. So please check email if you don't find your passport and come to the secretariat. Thank you. please be seated. Please be seated. I have two announcements to make. One is that the shuttle bus schedule for the return bus from your hotel to Naha Airport tomorrow has been updated. So if you are returning back to airport by taking the shuttle bus, please check again the shuttle bus schedule because it has been updated. And the second announcement is that, as I announced at the end of the previous session, we are going to move all the schedule half an hour earlier. So in order to avoid any confusion, I have written up the updated schedule here. And so if there is anybody who are not here, please let them know. And the last session, therefore, will start at 3:30 p.m. Thank you. So with that, I'm going to hand the microphone to Wati, who's going to chair this session.
Thank you, Hiroshi. So welcome to the new schedule version of the second part of the morning session. I'm happy to introduce the first speaker of the session, Jim Halverson, who will tell us about string theory and data science.
All right. Seems that the microphone is working. Thank you so much to the organizers for organizing this wonderful, wonderful conference and for the invitation to speak. It's great to be here. Today I'm going to tell you about a direction that has been developing a little bit over the course of the last year, though there were some papers about 5 years ago in this direction. And I am greatly indebted to wonderful, wonderful collaborators on a number of papers, some of which are out and some of which will appear. I'd like to highlight 3 of them. My colleague Brent Nelson has been central to the way that I've thought about this whole thing. We've been kicking this idea around for some number of years now at Northeastern and working on it intensively for about the last 18 months or so. I'd also like to point out the great job that Fabian Rula has done pushing a lot of this forward, both in his own work and his work with me. But I'd also really like to highlight, as you can tell by the bright green text, Cody Long, who is a postdoc at Northeastern, who has done a fantastic job on many different fronts. His breadth is really remarkable, and it's been a wonderful opportunity to work with him. I also emphasize it because he is applying for postdocs this year. If you're interested in this work or other aspects of his work, I highly recommend you look at his application. So this is interesting, trying to cover an entire different field in 20 minutes, 25 minutes. I'm not going to obviously be able to do all of it. On the other hand, I thought that it was not a good idea to focus on one particular technique within data science for 2 reasons. First of all, because the details would get perhaps unnecessary very quickly. And second of all, that might give the wrong impression that data science is just one type of technique, and that is definitely not true. Instead, I think a question that you might ask is, can data science or machine learning be useful for some problem X, broadly speaking? One thing that's interesting about this subject is that there has been a lot of media coverage over the last few years in this field because in computer science it's growing very, very rapidly. And the media coverage has a certain flavor to it. It is sometimes seems that the flavor is that X is everything, absolutely anything, and that the answer is that yes, it can solve anything. And that's of course not the case. But it is something that the media has caught on to, and one of the reasons is that though it can't do anything, there really have been non-trivial results. There is growth in this field within computer science for a reason, and there's growth in industry techniques for a reason, and so that's why it's getting covered. So if you want a more balanced view of this question, can data science or machine learning be useful for problem X, the right thing to do, in my opinion, is to ask a computer science colleague or to ask someone in industry who is a professional data scientist. So typical questions that you will get from them if you ask them this question at the top is something like, what does your data look like? Which is not something that we necessarily think of in physics right away. I should emphasize throughout that when I talk about data, I'm not necessarily meaning that you have an Excel file, boom, 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 here is all the data. Sometimes a construction algorithm for that data set is enough, even if you haven't constructed the entire set. So to this question, what does your data look like? There are good answers and there are bad answers. An answer that I gave very early on in talking to a computer science colleague is that my data is a 3-dimensional toric variety. And That got a little bit of a blank stare, rightfully so. And then I tried to explain it's kind of like a generalization of a weighted projective space, and that also didn't work so well. A better answer, which I think the rubric for how you give this answer is to ask how would you take your mathematical or physical data and actually put it on a computer. When you do that with a three-dimensional toric variety, what you really have is a set of sets of vectors in Z3 that are constrained according to certain conditions that are related to how they glue together in a fan in the toric variety and so forth. So what does your data look like is an important question that you'll get from them. But another question that you'll get from them is what are you trying to do or understand with it? That's part of the way that I've found that they want to know what technique they might be able to provide you that might be able to help with your problem. And that's part of the point. Data science is not one thing. There are a whole wide range of techniques that have started to work their way into our field. A lot of the things everything I'll talk about here is in string compactifications, but there's also a few examples in ADS, CFT, and quantum field theory. So this slide is really to emphasize that there are many different techniques and a number of papers on them. So if you're interested in this literature, this is the slide to look at later, but there are many techniques. So I have 3 goals in this talk. The first goal is just to tell you and show you that data science contains but is not equal to supervised machine learning. And if you don't know what supervised machine learning is, we'll get there. Don't worry about that now. But data science is more than that. So they have a whole suite of techniques, and we have many problems. And there's an order 1 question that we're still trying to figure out. Is there some useful map between the techniques that they have and the problems that we have? Broadly, one thing you might want to do with it, this is the second goal, is to use some of these techniques to tackle physics in the string landscape, because the string landscape is both enormous and complex. It's not one or the other, it's really both. One thing that you might desire when thinking this way is generally a better understanding of particle physics and cosmology in the landscape. I think we'd all agree that that certainly requires formal progress, but there's also this question of will smarter computer science techniques than we've used to date be necessary to really make progress in this direction? And at least it's my opinion and the opinion of a number of people that we probably need to be smarter with our computer science as well. A higher level view is the third goal. Basically, what I want here is for you to understand the broad ideas of what is possible in this context in case you're interested in taking some of these techniques and importing them into some other area in our field. Are there broader string or quantum field theory applications? So the outline of my talk is the following. I'm going to present a primary data set, which will be the only non-trivial data set that we deal with in this talk. It's a large ensemble of F-theory geometries. And despite the fact that it's large, I'll be able to tell you a lot about it and some universal features in it. I also want to emphasize that data science can be used for rigor. In particular, what we're going to do is use supervised machine learning to lead to a conjecture that then leads to a theorem. So we start with something numerical. It suggests something to us, and then we end up with a rigorous result by proving something about that thing that machine learning suggested. I want to talk about boundary detection using data science. I'll use something called deep reinforcement learning to probe the boundary of weakly coupled type 2B, and we'll see what that means. And then this last thing, which is very, very much in progress, I will present some modest results for low numbers of moduli of using deep reinforcement learning to find small cosmological constants in the Bousso-Polchinski model. And one of the reasons that's interesting is, of course, experiment. The other is that this problem is complex. OK. So with that introduction, here's the large data set. This is a data set of topologically distinct F-theory geometries that are connected in a Calabi-Yau moduli space. I'm not going to talk about it here, but in each of these geometries, there's a whole Bousso-Polchinski flux problem that you would put on top of it. But we're just going to study the geometries for now. And one of the things that's interesting about this is that even though the data set is large, there are some universal physical features that have been found in our ensemble and in other ensembles that are closely related by Wadi and Yinan Wang that really seem to be universal. OK, so the mathematics is the following. There's going to be a very, very useful, in my opinion, qualitative picture on the next slide that explains the combinatorics. But the mathematics is the following. We're in 4-dimensional F-theory compactifications. It's an elliptically fibered Calabi-Yau fourfold that is the geometry over some 3 complex dimensional base space B. The 7-brane structure at generic complex structure is determined by the topology of B, and these are called non-Higgsable clusters. This has been studied by a number of people in the last few years. So when we build our ensemble, our starting point for the ensemble is to take a weak phonotoric threefold B, encode it, which can be encoded in the structure of a fine regular star triangulation of a three-dimensional reflexive polytope. Other authors and speakers might appreciate the appearance of the polytope here. And what we're going to do with that weak phonotoric threefold is perform a number of topological transitions. We're going to systematically perform sequences of toric blowups over toric points and then over toric curves. That is something that can just be done. The sequences are bounded by some results in algebraic geometry of Hayakawa and Wang and applied in F-theory by Dave. Basically, there's a theorem that guarantees that if all of the singularities in the variety are canonical, the geometry is at finite distance from the bulk of complex structure in the Weil-Petersson metric. So what this does is that this bounds our sequences of blowups, and then you can classify them, which is exactly what we did. And over curves, there's this many sequences of blowups that you can perform, and over points, there's this many sequences of blowups that you can perform that satisfy a sufficient condition for canonical singularities. So basically what that means is given those sequences of blowups, which are little topological surgeries that you can do locally in the geometry, you can do each of them, perform all of them in all possible ways from some initial fixed triangulated polytope and build up a very large set. That's the math. One of the things that I really like about this is that there's a combinatoric picture. So in the picture version, this is our three-dimensional reflexive polytope that we'll be studying. This face here is triangulated right here, and in fact, the whole polytope will be triangulated. A fact is that any fine regular star triangulation of this polytope has 108 edges and 72 faces. And then what you can do is you can take these sequences of blowups, which are represented by little widgets like this or like that, and for every one of the 82 widgets of this type, you can stick one of them on any given little line in this triangulated face. And for any little triangle in here, you can take a widget like that and put it in. That's pictorially what is happening when you do these blowups. So the ensemble size is here. If you put the widgets on the triangulation, what you get is 82 to the 108, the number of edges, and 41 million to the 72, which is the number of faces, which is this large number. Here's the integer. Part of the point in displaying this is to emphasize this is an exact lower bound on the number of topologically distinct F-theory geometries. As Laura said, we know from results of De Cerbo and Sfaldi that the number of elliptic fourfolds is finite, but it's very large at least. And we actually know ways in which this set is an undercount. But it's a set that we can explicitly construct, really get our hands on, and derive universal results. I should say that there are other three-dimensional reflexive polytopes. Of them, there are 4319. There's one other polytope that yields the same number of geometries. They dominate the ensembles from the other polytopes by over 60 orders of magnitude. Okay, so despite the fact that the number is large, we can still actually do calculations in this ensemble by using the basic fact that often some geometric ansatz about this ensemble, where you can compute how frequently it occurs, leads to some interesting physics property. For example, in any given geometry, it's easy to compute the geometric seven-brane gauge group at generic complex structure, and you can do that. What you find is that these non-Higgsable seven branes, which are seven branes where there is no complex structure deformation that will split them apart, they exist with very, very high probability. Definitively, the probability is not 1, but it's close to 1 part in 10 to the 755. So it's very, very, very common that you will have these non-Higgsable seven branes. Finally, furthermore, you can also study universality of large gauge sectors. In this ensemble, you can find a geometric assumption that forces large gauge sectors on you. The probability, which isn't written here, is 99.99995%. And in that case, which I think is really an undershoot, the rank of the gauge group is greater than or equal to 160. And it has particular structure that is computable and knowable. One thing that you might think, if this is what a large ensemble of F-theory compactifications is looking like, is does this force us to think about cosmology in a way that might be a little non-standard with respect to some of our other friends that work on cosmology. For example, it suggests perhaps the existence of dark blue balls, which in one paper we argue might be a problem, but it's an interesting thing to look into further. Finally, the last thing that I would like to say is you might ask, how does weakly coupled type 2b fit into this very large ensemble? There is a geometric assumption that Cody came up with that basically leads to the fact that the number of these geometries that admits a weakly coupled limit, I should emphasize, at generic points in the moduli space, effectively all of these are strongly coupled. You can then furthermore ask the question, is there a weakly coupled limit in the moduli space or not? The number of such geometries that admits a weakly coupled limit, the probability is bounded from above by 10 to the minus 391. So this is something that we can say. It seems that F theory in general, at least in this ensemble, and Wadi's ensemble bears this too, has very, very large gauge sectors. Non-Higgsable 7 branes are generic, and strong coupling is also generic. Okay, so this is the ensemble. I haven't done any machine learning with this. Everything I just talked about was analytic. So what I want to talk about now is, can you get any rigorous results about this ensemble? So what we're going to do is a little bit of data science. We're going to do supervised machine learning. It's going to lead to a conjecture and then to a theorem. The physics application is whether or not you can get E6 in this ensemble. One of the facts about this ensemble is that E8, F4, G2, and SU2 overwhelmingly dominate the gauge groups that appear. Gauge groups that, if you were interested in this particular way, which is only one way of potentially realizing the standard model in the ensemble, you could go via SU3 or E6 on the 7 branes, but the fact is that those don't happen that often. We do have one way to random sample these geometries, and in those random samples, we found that E6 does occur, but the probability is something like 1 over 2,000. So 1 over 2,000 probability in an ensemble of 10 to the 755 is still a lot of examples. So what we set out to do, obviously we couldn't enumerate them all, we just wanted to understand how is it that this is arising. So what we wanted to do is, when E6 arises in the random samples, can we predict or not, when E6 arises in random samples, it's on a distinguished 4 cycle, that's a critical point, and then can we train a machine learning model to accurately predict yes or no for E6 on this distinguished 4 cycle? And if so, if the model predicts that, and with high accuracy it can determine it, there's a question of, can we learn then, turn it around, and learn how it makes its decision? So in our paper, we called this conjecture generation. After the fact, we learned that one of the CS buzzwords for this type of thing is intelligible artificial intelligence. If an AI learns something, can you learn what it learned in a way that's intuitive to you, which is a really important question, both for applications, but also for policy making having to do with artificial intelligence. So the basic point is that machine learning leads to a conjecture, leads to a theorem, means that we've taken numerical results and turned them into rigorous results. Here we go. So here's what we're doing. This is supervised machine learning. Supervised machine learning is the one that we all implicitly know best. The basic idea is that you're given a whole bunch of input-output pairs. And the goal is to have a model that learns to predict the output given the input, and then when tested on data it hasn't been trained on, it still predicts very, very well. What you want to do is see how well the model does. So the training data in this case is some particular combination of variables related to the details of the blowups. The output is whether or not E6 exists on this distinguished divisor. And this was a really simple example. All we had to do, we have this random sampler. We generated 10,000 random samples where E6 occurs and 10,000 without. So it's really a 50-50 split. And then we trained the model with a number of different techniques. The key thing to notice in this plot is all of these gold bars are the means, and they're always getting above 98% accuracy. So this is a pretty simple thing to do on your laptop. It took less than 5 minutes or so to train these models. It really wasn't that bad using a particular Python package. So this is a good thing. It seems that the machine can learn whether or not this particular feature related to E6 holds in these geometries. It can do it with very high accuracy. That's interesting in and of itself, but there's a question of whether you can then turn that around and turn it into something where we understand what's going on and not just the machine. So supervised machine learning implied, when you look under the hood and see how it's making its prediction, that one variable in particular was the linchpin. That fact led to a conjecture, which then led to a theorem, which was an if and only if condition for whether or not E6 exists on this distinguished 4 cycle. You might notice that I gave you a terrible slide with this totally unreadable theorem, but actually that was intentional because the details of this theorem are not the point. You can read them in our paper if you're interested, but the fact that the theorem even exists and came out of a machine learning setup is the point of this construction, of listing it there. So given this theorem, we can turn it around, do a probability computation. Because we now know what the conditions are, we can do a probability computation to determine the probability that this feature happens. And then given our ensemble size times the probability, we can predict the number of models that satisfy this. It's 10 to the 751. And then furthermore, you can test this probability against random samples. So what we did was we took 5 batches of 2 million random samples each. From the theorem, you would predict that there should be 1182 examples, and the random samples had 1183, 1181, and so forth. Very, very close to this. I mean, there's some statistics for the fluctuations around this mean, but this is showing that our theorem is working well. The basic point is that intelligible AI / conjecture generation can yield rigor. One thing that you might ask, which is a question I get a lot, is can you always do this? The answer is no. The basic rule of thumb is the simpler the machine learning model is, the easier it is to understand what it's doing and generate a conjecture. So in particular, artificial neural networks are great predictors, but they're actually often hard to understand. These are not the techniques that we used here. Next, I'd like to turn to boundary detection. In data science, there's something called reinforcement learning, which is basically a way to have your artificial intelligence do gameplay. The physics application here is to ask, what does weak 2b look like inside of this particular F-theory ensemble? So the picture of boundary detection that I have in mind here, suppose you have some interesting physical feature B and some interesting physical feature A that you're interested in understanding, and you have some robot in some very large complex space that wants to determine the boundary between feature A and feature B. It doesn't know the global structure of the space, but it does know how to determine in versus out. So in some cases, if the space is simple enough, random walking might be okay, like walking around this space. It's not so inefficient, but for high-dimensional complex spaces, or even two-dimensional complex spaces, it can be fairly difficult. So if this little robot is walking around in here, it's going to hit the boundaries very quickly, and it's going to be very hard for this robot to get down this little crevice right here. And if this is a particular interesting area of the ensemble, or if it's where the ensemble is dominated, this robot just has no way of getting there. So what you might ask is, can we reward this robot so that it learns how to not go out of bounds so that it can explore the space more intelligently? To do this, we're going to use something called reinforcement learning. This is my one-slide introduction to reinforcement learning. If supervised machine learning predicts, reinforcement learning explores or searches. Probably the most famous example of this is AlphaGo 0. So the basic idea, and in green are the buzzwords in the field, an agent interacts with an environment. It perceives a state from state space. It has a policy function that picks an action given the state, and then the action is executed, which takes you to a new state. When you end up there, you receive a reward, just like in behavioral psychology, just like the ideas from behavioral psychology. Successive rewards accumulate into a return. There's something called a discount factor that penalizes future rewards. It's one of the parameters of the model. And the basic point is that through certain feedback, the policy is optimized to maximize the reward. That is, based on how you set up the game, the agent learns how to act intelligently. So in this particular application, state space is my huge ensemble of geometries. The action space is to preserve is the sequences of point or curve blowups that don't immediately rule out a weak coupling limit. Remember, we're trying to ask what is the weakly coupled space inside of this ensemble. And the game itself is to start with one of these weak phonos, one of these triangulated reflexive polytopes, perform the sequences of blowups, put these widgets, put one widget somewhere on the geometry, check. If there is no weak coupling limit, we say, you're out of bounds, the game is over. If a weak coupling limit is still possible, we will give it 100 points and then repeat. And by doing this over time, the agent is going to learn how to explore this space more intelligently. I should say there's some implementation details here that I don't have time to mention. Critical to us is something called A3C, which is an asynchronous advantage actor critic, which is the particular reinforcement learning algorithm that we use. So here's the game results. First of all, what you should see on this plot is that this is the total number of training steps that the agent has taken. Each step is performing one of these sequences of blowups. And once in a while, it says, OK, I'm going to evaluate how my neural nets are doing in terms of helping me explore better. So every step it takes, remember, it gets a factor of 100 points. And this is the total score that it achieves before the game is over. So you can see that the scores are getting higher and higher and higher, where up here, you see that it's at a score of 9,500 or so, which means that it's learning to perform 95 sequences of blowups before it goes out of bounds. And the thing that makes this significant is that a random walker would be way, way, way down here. A random walker, we checked it, performs 3 or 4 sequences of blowups before it goes out of bounds. So we're able to get deep into this space that we wouldn't have been able to get into otherwise. And there's 2 preliminary physics results. The first is that weak coupling is very, very rare. My exponents got a little mixed up, but we have a lower bound of 10 to the 30 on the number of weakly coupled the number of geometries that emit a weak coupling limit, and it's bounded above by 10 to the 80 in this 10 to the 755 ensemble. The other thing is that a typical weakly coupled model is going to, in the weak coupling limit, have at least 30 SO8 7-brane stacks that can be typically Higgsed in complex structure. This is similar to, but a little bit different from to a model of Denef, Douglas, Florea, Grassi, and Katru, which I always thought was going to be pretty non-generic, but what we're learning in this ensemble is that there's typically a lot of that sort of structure. This was exactly the sort of structure that they had in that model. Finally, I'd like to comment a little bit on complexity in my remaining time. Basically, there's an interesting question, which is, can RL make progress on NP-hard problems? And I'm going to give very, very preliminary results at low moduli for the Bussel-Paczynski model. So the Bussel-Paczynski model, in a simplified version that Douglas and Denef studied, looks something like this. Your cosmological constant is some bare cosmological constant, and then you add to it something that is supposed to represent a flux vector, and there's some positive definite metric. And what they asked is whether or not there is a lattice point that gives a small CC in this above model, asking whether or not that's true is an NP-hard problem. Generally, though, NP-hard problems are very difficult, but there's this practical question, which is, if an NP-hard problem is really important to solve, and you care about concrete realizations, concrete parameters for that NP-hard problem, can you still make progress? So there is some progress in another model that I don't have time to really discuss in too much depth, but I highly recommend that you take a look at this paper of Ning and company that unfortunately I just learned about on Monday. One of the basic questions in this question of how to tackle computationally complex problems is whether it's better to use optimization, that is some sort of human-derived strategy that's model-dependent, or whether it's better to use something that's model-free. Basically, instead of using a human-derived strategy in that case, what you would do is teach the game and the machine learns the strategy. A priori, it's not clear which one wins. There are definitely trade-offs, and you should try both. Model-free reinforcement learning, generally model-free models are a good thing because you can apply them in many different contexts. And there is one famous case where model-free RL wins, and that's in AlphaGo. Okay, so there's a Bussel-Paczynski model. Basically, we're just stepping through this vector space. We draw metrics from a Wishart ensemble. Steps are to plus, plus, or minus, minus any vector entry. And basically, we're just asking the question, can we have lambda be sufficiently close to 0, but greater than 0 nonetheless? So the very preliminary results are right here. We have 2 plots for 2 sort of different models, just to show you that there are different sorts of behavior. The score, which is a sign of fitness, is this direction. How long it's been training is this direction. We have the max, the min, and the mean, so you sort of get a different feel for how these evaluation runs are going. But what you can clearly see is that it's learning to find cosmological constants. In this case, it seems to have flatlined a little bit, where in other cases you still have some noise that shows that it's still learning. That's 2 of the basic phenomena that you see. So in these contexts, I want to emphasize that the number of moduli that we have are 10 and 25. So Bussel-Paczynski, when we normally talk about it, when we talk about a large landscape of small CCs, we're typically thinking hundreds of moduli. So we're just starting with a simpler problem, seeing how well we can do on the simpler problem. And what we find is that it basically learned 5 or 6 orders of magnitude in the CC through evaluation runs. Our best right now is 10 to the minus 15. We tried some other things too. There's sort of this open question that we don't know the answer to yet. Is the fact that we can't do better than this, is it something that is fixed because we're at low moduli, or is it something where we're just not using quite the right techniques yet? And that's still an open question. So the question is, will learning stop here or continue to smaller cosmological constants? Can we get improvements at higher moduli, as we expect for Bussel-Paczynski? And for that, I encourage you to stay tuned. So string theory and data science, thank you for letting me take you through this sort of wide variety of things in 25 minutes. I wanted to emphasize that supervised machine learning is wonderful and useful, but data science is much, much more than that. And the three things that I emphasized is that you can get rigorous results by taking some machine learning result, turning it into a conjecture, and proving a theorem, which in this case was about E6. You can also have boundary detection type problems where you use reinforcement learning to sort of stay in bounds. I told you properties of what weakly coupled type 2B looks like in this ensemble from those techniques. And I also started to discuss issues of complexity where model-free reinforcement learning on NP-hard problems was used to find small-ish Boussel-Paczynski CCs. So all of these are interesting, and a few of the papers are out. A few of the papers should be out in the next few months. And please ask me questions if you have them. To finish, I think it's important whenever we're trying to import techniques from another field to remember impressive results from their field. And the finish is a brain teaser. In what 2015 movie did this pair co-star? And the answer is they didn't, because these people don't exist. So when I first saw this result, I thought it was pretty shocking because I found these images pretty convincing. In fact, these were generated by what's called a generative adversarial network, which is one of the other major breakthroughs, yet another technique in data science from the last 3 years or so. All right, thanks for listening.
Thanks, Jim, for a nice talk. So we have time maybe for one or two quick questions. Elias?
You mentioned many gauge groups that arise in these constructions.
I did.
And I presume when you talk about strong coupling, you're talking about strong coupling at the string scale or compactification scale?
Yes.
What about at low energy? Can you tell how many of them would have weak coupling at low energy?
Right. So there's a flux story that I didn't tell here. Sort of the order one answer is that if you don't turn on fluxes, you're typically going to have pure super Yang mills, and that's going to confine and it'll be strongly coupled to low energies. The coupling that I was talking about was the string coupling. Yeah.
Maybe one more, Edward.
This is kind of a left field question, but I gather that in real neuroscience, when an organism is exploring its environment,
Yeah.
there are these grid cells which fire at lattice points they've discovered in the region. They also deal with how does it know about the boundaries and so on. I'm wondering if this plays any role in machine learning when you try and map out the geometries the way you are.
That is an interesting question. One other context there is that people ask the question, do neural net architectures do better when they more closely mimic biological neural net architectures? And that is something that people study extensively. I don't know too much about it. In this particular context, we use a couple of different very simple neural net architectures that weren't doing anything that fancy. The basic mechanism isn't using an architecture like that, which might do better, but it's basically just using this idea of a reward to learn how to do better. But it would be interesting to try to do that, but then you really have to get into the guts of the neural net architecture.
Good. I think Edward had a
Yeah, my question was if you can tell us anything about the ultralight axions.
Oh.
What light would they be, and what do we have to get them?
Well, you had a very influential paper a few years ago about the ultralight axions. Presumably, you're asking about this because you saw this comment on my slide. Yeah, so generally in these models with large gauge groups, it's not fully determined, but there is a real concern that with many, many gauge groups, you're going to oversaturate the dark matter relic abundance. If you don't, if it's about an order 1 fraction of the relic abundance from these dark glue balls, the result that we had recently is basically that the natural axion that you would get from the gate associated with the gauge sector is going to be of roughly the ultralight scale. So if you have a dark glue ball that is playing a non-trivial role in the relic abundance and you consider its associated axion, it's going to typically drop you near the ultralight scale.
Well, I'm not sure either what you mean by the axion associated with the glue ball or the ultralight scale.
By the ultralight scale, I mean order 10 to the minus 22, 10 to the minus 20 eV. By the axion associated with the glue ball, what I mean is that there's a dark gauge field strength, G wedge G, and some axion is coupling to it. That's the axion I mean.
Okay, this raises a lot of questions, but I won't pursue it right now.
Okay, I'd enjoy talking about it.
Okay, great. Let's thank Jim again. And now I'll introduce the second speaker of the session, Irina Valenzuela, who will tell us about the swampland, field distances, and naturalness.
Okay, so first of all, thank you very much to the organizers for the opportunity to speak in such an amazing conference. I have to say it's very challenging to talk the last day because you've been the whole week listening to fantastic talks and you think, wow, I really have to give a very good talk to keep the high quality level. So I will do my best. And I hope that at the end of the talk, I will be able to transmit to you two messages. First, that, well, I think it's very exciting just the existence of the swampland, that not everything is possible, because then it means that it has the potential to give rise to non-trivial constraints and implications for low-energy physics coming from string theory. And second, that it's a very important task then to gather solid evidence for these conjectures and these ideas. And this is something that I think it can be done, and that I want to show you that all these conjectures are not just hand-waving arguments, but sometimes can be translated to very concrete statements that can even be checked, and I think that's beautiful. And it's our job, I think, to make this happen. So let me start by saying what's the swampland. So the swampland are those effective quantum field theories which look apparently consistent in the sense that are anomaly-free, but still cannot be embedded in an ultraviolet completion in a consistent theory of quantum gravity, like string theory. So the idea is that if you have all possible effective field theories that you could construct, not all of them can arise from string theory, but only a subset, which is called the landscape, and the ones that cannot arise are said to belong to the swampland, because they present some inconsistency with quantum gravity. Now, I think, as I said, this is great, because not everything is possible in string theory, which makes string theory predictive in some sense. So I mean that if the swampland didn't exist, so if every quantum field theory that we could construct would also be constructed in a string theory, then it would be impossible to have any prediction from quantum gravity or any implications at low energies. But this means that we can have additional constraints that corresponds to some UV imprint from string theory. So the million-dollar question, of course, is what are the constraints that an effective theory has to satisfy in order to be consistent with quantum gravity? So what distinguishes the landscape from the swampland? And I think this question is, in a spirit, similar to understanding also the anomalies in a gauge theory. So what are the conditions that are necessary in order to ensure quantum consistency? And it's just that when we couple the theory to gravity, it seems that we get something, or some more rich or more constrained set of constraints that go beyond at least the way we understand anomalies now. And the question is, what are they? So there are some proposals. And these proposals are motivated usually by studying recurrent features of the string landscape, and also based on black hole arguments. And I think it's very important to remark that these proposals go under the name of quantum gravity conjectures, because none of them has been completely proved in complete generality yet. But it's also fair to say that with the years, we are gathering more and more evidence in favor of these conjectures. So the typical two examples are the absence of continuous global symmetries, not associated to gauge fields, and the completeness hypothesis. But also in the past years, there is a lot of activity regarding these other ones. So we already heard about the gravity conjecture on Wednesday, and the controversial debate about the sitter on Monday. In this talk, I want to focus on the swampland distance conjecture that I will explain in a bit. But before that, let me just remark the first message, that a very interesting feature is that these conjectures have the potential to have non-trivial implications in low-energy physics, especially for theories which are UV sensitive, like large field inflation, but maybe also for issues related to naturalness and fine-tuning problems. So maybe this is not so obvious why. So before going into the swampland distance conjecture, I would like to, well, I thought I should say some words about also this project of how, in fact, we can get constraints on, well, on the electroweak hierarchy and the cosmological constant from this other conjecture. So I will just use 2 slides and then move to the main part of my talk. Okay, so the point is that, well, very recently, Oguri and Baffa argued, inspired by the weak gravity conjecture, that non-supersymmetric stable ADS vacua are not consistent with quantum gravity. So they should belong to the swampland. If we take this for granted and we apply it to our standard model of particle physics, there is a problem, because if we compactify the standard model to lower dimensions, we can get anti-de Sitter vacua, which are non-supersymmetric. And if there is no instability in this vacua, which might happen if the bubbles that we could have in 4 dimensions are too big, then that would mean that the standard model itself would be inconsistent with quantum gravity. So one option is to require the absence of this vacua, which means to put constraints on the standard model, because the presence of the vacua is just a balance between the value of the cosmological constant and the Casimir energy from the standard model particles. So the bounds, well, this is a work I did with Luis Ibáñez and Victor Martín Lozano. So one can get an upper bound on the neutrino masses, which means that ADS vacua don't appear if the neutrino masses are lighter than the order of the cosmological constant, which is the numerical coincidence observed in the universe. It's also possible to get constraints on beyond standard model spectra, and Luis continue and studying other compactifications. One can see that one would even know, what would need some extension of the standard model, like supersymmetry, in order to avoid this vacua. So these constraints are not necessary constraints in the sense that could be that there are some other instabilities, not clear if these vacua are stable or not, but are sufficient conditions in the sense that you just avoid the presence of the vacua. And I think the interesting thing is that they precisely explain what are the hierarchies that we observe in the standard model. So just a comment that this upper bound in the neutrino masses could be translated to an upper bound on the electroweak scale. This conjecture would imply that the Higgs vacuum expectation value has to be smaller than this. So if we happen to live in a universe with a small cosmological constant, also the electroweak scale has to be small, because parameters leading to higher values would not be consistent with quantum gravity. So there would not be an electroweak hierarchy problem in that sense. Now, this is not a solution of the electroweak hierarchy problem, because there are many assumptions here. It's just, I think, an example that shows how maybe we have to modify our intuition about fine-tuning and hierarchy problems in the presence of gravity, and how naturalness maybe is not a good principle and could be just an artifact because we don't know what is the actual landscape of consistent theories. But so I could continue talking about this, so you can ask me later, but I want to move on to the main part of my talk, because I'm sure that most of you are thinking this is very nice ideas, but as long as they are just based on the conjectures and we don't get more confidence about these conjectures, we cannot really do a serious prediction coming from this. So what I want to show you is that we are going to focus on this swampland distance conjecture, which has implications for inflation. And what we will do is, this is a work I did with Thomas Grimm and Eran Party, is to check this conjecture in some specific moduli spaces and really try to understand what is going on there and get solid evidence for that. Okay, so let me start defining what is the swampland distance conjecture. So this is a conjecture that appeared already in the original paper of Oguri and Baffa, and says that any effective field theory, which is consistent with quantum gravity, is only valid in a finite region of the moduli space. So it's valid only for a finite scalar variation, because an infinite tower of states become exponentially light in terms of this scalar field variation when I move very far away in the moduli space. More concretely, if I have some moduli space of an effective theory, parameterized by the vacuum expectation value of the scalar fields, the kinetic term describes parameterizes the metric, and if I consider an effective theory valid at a point in the moduli space, and now I move to another point, the effective theory here, compared to the theory here, will contain an infinite tower of particles whose mass decays exponentially on the geodesic distance between the 2 points. Okay. So the fact that we get infinitely many fields signals the complete breakdown of the effective theory. And this has implications for low energy physics because it's relating to quantities which in principle in quantum field theory are disconnected, which is the field variation and the cutoff in energies. So if we want to have an effective theory valid for some field variation, this means that the energy of the process that we can describe with this effective theory is lower than the naive expectation in the absence of gravity because of this drop-off of the cutoff. So this gives an upper bound on the scalar field range in terms of the cutoff, so relates both things, and has implications for instance, for large field inflation, because there we need both a high energy scale and a large field range, independently on what is the scalar which is playing the role of the inflaton, in principle. And there is a lot of debate whether this really forbids transplanckial field ranges or not, like when this happened. There are some arguments and many examples are compatible with that, but there are caveats because it's not clear if one can really generate mass hierarchies or move along other trajectories so that one can delay this effect. But my point is that I think this is very difficult to settle, to answer this question, because so far, all the evidence we have for this conjecture, in fact, just comes from studying particular examples in string theory. So this, I don't know, we didn't really have, at least me, a clear understanding of what was going on, what was giving rise to this behavior, in order to see if it was really happening at the Planck scale or not. And also very little is known about this tower of particles. And in most of these papers, we were always using just a Kaluza-Klein tower or something like this. But in principle, it should apply to any scalar field. So what we did is try to improve these points by giving a step backward. So we decided, okay, let's take the complex structure moduli space of a type 2B Calabi-Yau threefold compactification, which is a 4-dimensional n equals 2 moduli space, preserving special Keller structure. So these moduli spaces are very well understood. And let's check the conjecture there. If we can really get these infinitely many particles for any infinite distance path that we can have. Okay, so let's do it. So the first thing to notice is that in order to get an infinite distance, I need to approach a singularity of the moduli space. And precisely at these singularities of the moduli space, it's known that we have BP states corresponding to DC branes, wrapping the cycles that shrink, becoming massless. Okay, so these states are perfect candidates for this tower predicted by the Swampland distance conjecture. And now the question is that, well, these singularities can be at infinite or a finite distance, depending whether any trajectory approaching the point has infinite length or not. And the question is whether at these infinite distance singularities, we always have infinitely many fields becoming exponentially light. So our aim is to identify an infinite tower of exponentially massless BP states at any infinite distance singularity of these moduli spaces for any Calabi-Yau. And the way we do this is by studying the monodromy transformations around these singularities, because this monodromy transformation will precisely identify whether the singularity is at infinite distance or a finite distance. So we will see that the infinite distance singularities are characterized by having, well, we need to have some monodromy of infinite order. And then we can use this monodromy of infinite order to populate infinitely many BP states. So in order to do that, we will use some mathematical theorems about the geometry of the moduli space, very powerful, and also techniques which are known about counting BPS states. And I will show you how this works. And then once we have this set up, very concrete and very clear, we can also use it to extract some information about what is going on and what is happening here and what can be the underlying reason of the conjecture. So we see that these points are characterized by restoring, in principle, some global symmetry. And the infinite distance itself can emerge, in fact, from integrating out the infinitely many fields. So in this paper, we focus only on points that belong to a singular divisor. So that's what I will talk here. And for the future, we are now studying what happens at intersections and higher singularities. OK. So let's see how this works. So in order to measure the distance in the moduli space, I need information about the metric, which, because of the special Keller structure, is given by the Keller potential, parameterized in terms of the periods of the holomorphic D,0 form. And these periods undergo a monodromy transformation when I circle around the singularity. Okay, this is the monodromy transformation. And now, the point is that if this monodromy transformation is of infinite order, okay, then I can define a nilpotent matrix in this way. And there is a very powerful theorem by Smith, which is the nilpotent orbit theorem, which tells me that for any Calabi-Yau, the periods near these singularities have always this universal expansion, which means that the leading term is determined basically by this nilpotent operator. And then we have subleading terms which are exponentially suppressed with respect to the leading one. Okay? Now, if this leading term is non-vanishing, so this leading term will give rise to a polynomial in T. So T is the variable that I use to parameterize the moduli space so that the singularity is located at imaginary part of T infinity. So imaginary part of T is the radial coordinate to approach the singularity. Then, if this polynomial is not vanishing, when I compute now the metric near these singularities, they always have a universal form. So the leading term is always given by this. It's just 1 over the imaginary part of T squared. And this small d is just the degree of the highest degree of the polynomial. Okay? Now, if we have this form for the metric, then this automatically means that these points will be at infinite distance, because now if I compute the distance when I approach the singularity, it will diverge. So this is a theorem that the point is at infinite distance if and only if this monodromy operator exists and n times x0 is different from 0, which means that I have this polynomial, that the polynomial is not vanishing. So infinite distance only occurs if the monodromy is of infinite order in particular, which means that this n is non-vanishing. And now we can use this monodromy to populate an infinite orbit of BPS states, because, well, in general, so the mass of the BPS states will be given by the central charge, and in general, the central charge will not be invariant under the monodromy transformation. But the whole theory has to be invariant, because this monodromy transformation cannot give rise to a change, a physical change. So what is going on is that the tower of states reorder itself. So when the mass of an individual state changes, another one within the same orbit takes its place. And then in the end, the individual states are not invariant, but the whole tower is. Okay? But this means that if one of these charges is populated by a physical BPS state, then all the states in the tower also must be populated by physical states. So if the monodromy is of infinite order, just starting with 1, we can generate infinitely many. And if they are massless, so if they become massless at the singularity, which is also given by this condition when we plug this nilpotent orbit theorem on the central charge, the universal form of the metric will imply that the mass of these states always become exponentially light in terms of the proper field distance when we approach the point. Okay? So the exponential mass behavior is just given by the local form of the metric, and then all we need to show is the existence of this massless monodromy orbit at the singularities. So the Swampland distance conjecture, in this case, is reduced to prove just the existence of a charged state which satisfies these two conditions, so it becomes massless and can generate the infinite orbit. In order to do that, I will not go into the details of this, but we use all the machinery of the Mishot structure, develop at these singularities, which introduce a finer split of the cohomology, adapt it to this monodromy operator, and check that these two conditions can be satisfied. I just want to say some words about what happened with these BPS states when we are approaching the singularity, like how many BPS states we have, which is translated of whether they cross any wall of marginal stability when circling around the singularity. So we can study the grade of the central charge, and we can see that the grade remains basically constant as long as this order, so as long as the charge is small enough comparing to the imaginary part of this, so how close we are to the singularity, which means that from the whole orbit, so all the BPS states that become massless, only there is a threshold below which they are stable and above which, higher up in the table, they are unstable, which implies that when I am approaching the singularity, the picture is that the number of BPS states is exponentially increasing in terms of the proper field distance and diverges there. Okay, so very nice. We have a very clear realization of this conjecture. And now we can wonder what we can learn. What are the general insights and intuition that we can get from this? So first of all is that precisely at these singularities, this monodromy transformation corresponds, like from the point of view of the field theory, to a discrete shift symmetry for the axion, like the angular variable. And at the infinite distance singularities, this discrete symmetry can be enhanced to a continuous one. This only happens if the point is at infinite distance. So one could imagine that, of course, at these singularities, the cutoff goes to 0. So the Swampland distance conjecture is, again, a quantum gravity abstraction to recover this global symmetry, this global axionic shift symmetry that we would recover at the point. And this is very analogous, in fact, to the weak gravity conjecture, because, again, all these conjectures are kind of quantifying how close I can get to the situation of recovering a global symmetry. So for the case of the weak gravity, it's related to the gauge coupling. So the cutoff of the theory has to be smaller than the Planck mass times the gauge coupling. So I cannot make the gauge coupling very, very small. And the cutoff also goes down in the same way. And for the Swampland distance conjecture, the same happens, but now it's with the scalar field variation. Okay? So the cutoff also goes down when the scalar field variation becomes large because I would recover a global symmetry. There is also an electric version for the Swampland distance conjecture, so we can imagine that it is some sort of scalar with gravity conjecture, so the scalar force is weaker than the gravity force, and this would give some hint of, in order to satisfy this equality, we need precisely to have an exponential mass behavior for the particle. Now, the second thing is that, it's known that not only the singularities are, the consequence of having these BPS states becoming massless, but also the geometry around the singularity can be understood in terms of integrating out these BPS states. So this is something very well known, for instance, in the coniform singularity, in which the divergence of the gauge coupling can be understood from integrating out a single BPS DC brane state. So we do a very similar computation, but with this infinite tower of states, and recover, compute the one-loop quantum correction from integrating out this tower, and see that it matches the geometric result. Okay, so this is just evidence for the existence of these infinitely many BPS states at this point. Okay, I just want to say that in order to do that, it's very important, in order to recover the geometric result, it's very important to take into account that the number of BPS states is increasing when we approach the singularity. In other words, that the cutoff is decreasing. And this has also a very nice interpretation in terms of field theory, because this growth of states can also be understood if we are integrating out the tower up to the species bound. Okay? So in principle, when we have many light particles, the Planck mass will get renormalized. so that the cutoff goes to 0, you have infinitely many light fields. And precisely because this tower is getting compressed when I reach the singularity, the number of states below this species bound is increasing, and just, this behavior of the delta M gives rise to a field-dependent cutoff, which goes to 0, and this matches with the growth that we obtain by counting the BPS states. Okay, so just to finish, this means that this species bound, if we take this species bound as the UV cutoff, it precisely goes to 0 exponentially in terms of the proper field distance, according to as the swampland distance conjecture says. And we can also do the same for the gauge kinetic function. So in the same way that for the field metric, we recover the geometric result and the infinite distance, we can also recover that the gauge coupling goes to 0 at these singularities. So the infinite distance and the weak coupling emerge from integrating out the infinite tower of states. And then one can wonder whether this is a general feature or not. So from here, I don't have the answer, because we just studied these modular spaces. But it's an interesting question, at least what is the specific structure that this tower needs to have in order to give rise to the infinite distance, and whether infinite distance always appears from integrating out the states. So I don't have time to discuss it, but the important thing in fact is just to have this compression of the tower and integrate out to the species bound. And I said also that there is a continuous global symmetry appearing at this point. So if the infinite distance is emergent from integrating out the states, also the global symmetry might be emergent from this integration out. And we can see that precisely because the number of states goes to infinity, and this implies that the cutoff will go to 0, and the only way then to have a global symmetry in an effective theory with a finite cutoff would be to decouple gravity. So let me just summarize. So we check this swampland distance conjecture in this modular space. It would be very nice to think about other modular spaces and see how general or how general these ideas are. And just that, well, let me say again that consistency with quantum gravity can have implications for low energy physics. And therefore, it's very important to gather more evidence for this conjecture, which is, I think, a doable and very exciting task. So thank you very much.
Thanks very much, Irina. Nice talk. So we have time for a few questions. Daniel?
Hi, so I just want to make a comment about your motivation. So, so in the ground state of the simple harmonic oscillator, the particle could be anywhere, but that doesn't mean that we don't have any information about where the particle is. And so similarly, I would say, so you said in the beginning of the talk that having a swampland is necessary for string theory to make predictions about low energy physics, and I think that's false.
I don't think it's necessary, I think it's useful.
Useful, yeah, but yeah, you said necessary. You said otherwise we wouldn't be able to make any predictions.
Ah, okay, I know what you mean.
Yeah, so I think that's false. I think it's better to say that what we need is some sort of probability distribution on the space of low energy effective field theories. And of course, the simplest thing is that it's 0 on a bunch of them. That's the swampland, right? But I see no reason why that should be. That's neither necessary nor probably true. In general.
Yeah, you can also have arguments instead of probability, what is more likely to have or not.
Yeah,
but it's just
that's enough.
It's stronger. Yeah, if
I
can say this is not possible.
I mean, yes,
it's
please,
clear
if we can have it. Yeah, it's just we don't need it.
Okay, it's fine.
I can't help but interject briefly that there is a sense in which the swampland is kind of a time-dependent thing. There's a set of constraints we know from low energy, and there's a set of string construction, and finding things that appear to be in the swampland lets us better understand both more constraints from energy and string.
No, absolutely, we should do it.
Yes.
Yeah, I'm working on it too.
Yeah,
we should be clear about what we need.
It's about the non-supersymmetric ADS value.
Gravity limit. Clearly, there are non-supersymmetric field theories which would have stringy ADS duals.
I didn't go into the details of that, but the statement is that you cannot have ADS whose gravitational sector is just weakly coupled Einstein gravity. So that you cannot have if you have a non-supersymmetry CFT, that of course there are non-supersymmetry CFTs, it cannot satisfy the large N and large gap at the same time and have an ADS dual, which is Einstein gravity.
I mean, you could probably still have large N theories, just they're weakly coupled, and they would have stringy duals. That's certainly reasonable.
Yeah, probably they would have parametrically light higher spin fields or other things. Yeah, sure. But the question is, I mean, from the point of view of field theory, I mean, if I want to have an effective theory describing low energy physics, the standard model, extensions of the standard model, it's interesting the question of what effective theories can make sense. I mean, which ones I would be able to embed in the UV in the string theory or not. And then I have large N and large gap.
Eva?
So I just want to make a quick comment and a quick question. So this motivation of understanding large field inflation better is wonderful. But it does happen that in the original constructions of that, this question of what is becoming light as you go the finite distance that you need was very much part of the analysis. So yeah, there was this kind of wind-up toy description in some duality frame, and what's getting light there is strings that go between the windings of the brain, if you like. And I want to make two comments about it. One is, especially in the high-scale examples of that, you know, it wasn't winding up enough for that to be an issue within the sort of order 10 Planck units that were needed. In the lower supersymmetry breaking scale examples, I mean, one thing I want to emphasize is that even when, say, those n-squared strings are getting light, and say they build up a order 1 Tuft coupling, well, we know what that is. That's actually its own little brain throat, and it sources a certain tension. So it's not always a tragedy if, in fact, you get into a regime where your weakly coupled effective description starts to fail. You might still have tools. So
I think I mean, this conjecture is giving you this relation between the large field and that something will fail. Now there is for phenomenology, the interesting question is how bad is that? And that's what you are saying. It's a debate, and I guess it depends. So we can start taking different models and then try to check in each model like when they become light and then when the effective theory will break down. My point of view is that in order to give any general statement, we need to understand why this is happening, and maybe
I have no issue with the fact that it's happening.
Yeah. So I agree. I don't know when this will happen, if it will happen at the Planck scale, or there can be models in which it cannot happen. I hope to be able to answer by that, not just by studying particular models, but by having a broad perspective.
But particular models in which it's already been seen that that it doesn't come down very much within the needed range, needs to go into that sort of statement. My question was, in your analysis here, do you have effective axion degrees of freedom which always have light superpartners in this system you were studying?
Well, here we have n equals 2 supersymmetry. So yeah, it's always the hypermultiplet.
Okay, so another brief comment is that I think generically stringy axions occur without having light superpartners, stronger supersymmetry breaking examples. So it's important to cover that case as well.
Yeah, I mean, in principle, this should apply independently of supersymmetry. So it would be very nice to study other cases in which one doesn't have n equals 2, lower supersymmetry, or even none.
Great. Maybe one more quick question from Andy.
So there are people here who could correct me if I'm wrong, but my impression was that sort of between 1970 and 1985, there was basically one compactification of string theory known, the torus. And then in 1985, it mushroomed by many, many orders of magnitude. Then from 1985 with Claviao, and then various other kinds of different bundles and so on. In the next 10 years, it again grew another 10 orders of magnitude. And then with flux compactifications, from now it's again grown hundreds of orders of magnitude. Why on earth should we think that we've come to the end of this process? And by surveying the kind of compactifications we've already understand, we can understand what string theory has to say about what is possible. And why should we think that there's in fact any difference between what string theory, in the largest possible sense of the word, can produce and what is allowed by low energy effective field theory?
Okay, so It's a very important question and difficult to answer. I think the message, or why I find this so exciting, is that the landscape can be huge, even bigger than we think now. But I think that we don't have to get pessimist in that sense, because I think it's possible to get information about what is possible or not, I mean, the string theory, without knowing all possible theories that belong to the landscape. And that would be possible if we are able to understand what is the underlying quantum gravity obstruction of this conjecture, and not just formulating the conjectures by checking examples, because then we don't know, I mean, if we are just looking at the lamppost or not. So I'm trying to find, I don't know, some principle in the same way that we have anomalies, something like this for gravity.
But that's low energy considerations, anomalies.
Yeah, but it's like anomaly in the sense that does not depend on the scale. So these are constraints that have an impact on the infrared, because, I mean, they tell you that in the UV you will not be able to embed it in quantum gravity. But I agree it's a very, very hard question to distinguish whether we are just looking at the lamppost or not, and whether these conjectures are just a problem of having only a reduced vision of what we have. But I think at least would be very interesting to be able to define this with the knowledge we have so far of string theory. Maybe it has to be changed in the future, but...
So these are great questions for further discussion. We can return to some of this afternoon, but I think let's thank Irina again for a great talk.
Okay. Sorry? Yeah.
Okay, great. And the final speaker of this morning's last session is Eva Silverstein, who is going to tell us about de Sitter holography and entanglement entropy.
Okay, let me add my voice to the very unoriginal but quite correct thanking of the organizers for this wonderful meeting. It's been incredibly interesting and stimulating. I would like to discuss a subject which kind of spans a couple of topics that have been covered here to some extent already. And it's based on a recent paper with Shidong, who is here, and Gonzalo Taroba, wonderful collaborators. Also based on a whole sequence of earlier works with this larger wonderful group: Hussein Al-Shahia, Bart Horn, Andreas Karch, Shunji Matsura, David Tong, and Gonzalo. Okay, so I intended to show one of these at a time, but this is fine. So what are the motivations? Well, here they are in extreme experiment and extreme theory. So accelerated expansion fits the observational facts very compellingly. In the late universe, we have multiple probes of the so-called dark energy, starting with the supernova data, but also including the CMB, BAO, et cetera. In an early universe, in a highly non-trivial way, inflation, the paradigm of inflation fits extremely well. Again, it's multiple probes, the WMAP and Planck, Planck with both temperature and polarization, fit the same exact 6-parameter model to very good approximation, up to little tiny deviations they worry about with Hubble now. So it's extremely precise. And it's just the case that accelerated expansion dominates in our world. Now, I would argue that at least it should be uncontroversial that positive potential energy, at least, dominates in string theory. So if you think about the classical sources that we have, the leading term in the potential is the D minus D critical term, which is positive. Even if you turn that off, most compactification manifolds have negative curvature, and that contributes positive potential energy at tree level. And certain fluxes, like NS fluxes, also do so, and so on. You have to turn a lot off to get to the positive curvature, negative potential of the beautifully simple Freund-Rubin solutions. that give ADS solutions in combination with Ramon fluxes. The simplest possibility for DS, which is involved in all of the proposed constructions, requires in this kind of direction of the inverse volume and also the string coupling, involves at minimum a kind of three-term structure where in addition to these dominant positive tree-level terms and say Ramon flux, which is also classical but occurs in the expansion in string coupling and in volumes, gets diluted. There needs to be some intermediate term that produces a dip in the potential. And Polchinski et al.'s orientifold planes are beautifully suited to do this. They appear subleading in the expansion in G string, and they can be dilute sources and therefore also appear subleading in the expansion of inverse volumes. So now this is not an innocuous statement. It is very complicated. We all know that. Perhaps I'll say a little bit more about that this afternoon, but the whole interpretation of the dark energy in terms of this sort of picture requires it to be complicated. It wouldn't make sense if it were too simple. But many of us are quite persuaded by the arguments for these mechanisms, starting from the ones that use the leading positive term in the string theory potential, as well as the beautiful work of Giddings, Kacu, Polchinski, taking care of the complex moduli of Calabi-Yau compactifications, completed by KKLT in 2003. And this year we're celebrating the 15-year anniversary, 1.5, of KKLT. I think Sandeep has left. He's the only representative in this meeting of that, but it's something to celebrate. So there are various versions of this sort of scenario. They all have this sort of structure in some directions and a two-term structure of flux stabilization of dual cycles and axion stabilization of dual cycles in other directions. Now, we did bother to produce a explicit example building up from the D1, D5 system, the ADS3 times S3 times T4 geometry for two reasons. One, to try and make this more explicit, and also, as we'll focus on here in this talk today, to see what happens to the ADS-CFT duality when you add sources that change it, that uplift it from ADS to DS. In this, doing it in the minimal possible way. So what we'll find is a really interesting pattern that's quite concrete that makes use of this metastability and gives us a framework for de Sitter holography that we'll explore further in this talk. Okay, so we went through real experiments. What does the string configuration space look like? And then, of course, thought experimentally. Back in the 70s, there was brilliant work by Hawking and others, in particular de Sitter, Gibbons and Hawking, working out these thermodynamic behaviors of gravitational systems. In the de Sitter case, there's this Gibbons-Hawking horizon entropy. If you have an observer here. So throughout this talk, I'm going to consider a D plus one-dimensional de Sitter space. We're going to be interested in a holographic description based on a D-dimensional theory. And then the Gibbons-Hawking area in G Newton or G Newton units is then a D minus one-dimensional volume. So this is a Penrose diagram for de Sitter. Every point, except for the poles here, is a sphere, and this one in the middle is its area gives the horizon entropy for an observer on the right-hand side of this picture. So, this entropy, much like the black hole ones, demands some kind of quantum gravity interpretation, ideally some kind of microscopic interpretation. And of course, more generally, we would like, a dream would be a complete quantum gravitational framework for the positive potential, the generically positive potential landscape string theory. Okay, so the point of this talk eventually will be to, first of all, what I'll do is I'll review a framework for de Sitter holography that we've been developing over the years, and then add to that duality a very basic analysis of its, if you like, its quantum information content, so its entropies, the state, features of the state that it has, And in order to get there, I'm going to go back to the basics of the framework, but let me first flash one of the punchlines. So as Xi reviewed in his talk, and we heard from Xiaoliang also, there's this wonderful example of a thermofield double state of two CFTs that aren't interacting at all, and yet the gravity side of that involves a joined space-time. So there's an entangled state of the two non-interacting CFTs, and there's a lot of evidence, going back to Juan's arguments, that gravity side at moment of time symmetry, I've drawn a spatial slice, is joined. And so there's this is one of the many reasons that people conjecture that in general entanglement has something to do with knitting together different parts of space-time. So one aspect of what we're going to do today is to find that de Sitter gives us an analogous statement, somewhat analogous, where there's a joining of two parts of space-time. In this case, this sphere I'm drawing here is the sphere at tau equals 0, or the middle time slice of this Sitter-Penrose diagram. We'll see why it's divided into two, and there will be entanglement between the holographic duals corresponding to the two sides of this, which will give us an analogous statement. Let me get there step by step. Okay, so the statement is going to be that de Sitter in D+1 has a formulation in terms of two coupled, cut-off, d-dimensional DFTs, which are constrained by a residual gravity that does not decouple, d-dimensional gravity, again, starting from D+1 dimensions. And I'll show you that this, admittedly, it's a concrete but not completely precise statement, that it follows from 2 + 1 independent arguments. You'll see why I say 2 + 1 shortly, including a macroscopic argument, just based on the geometry of de Sitter space time, and a more microscopic argument. So let's start from the macroscopic one. So our original observation in what we call the DS-DS correspondence is to take de Sitter space and anti-de Sitter space, and first of all, just consider a slicing of those into lower dimensional de Sitter. So here I've written the metric of either ADS or DS in D+1 dimensions. It can be realized as a warped compactification down to de Sitter D. Of course, in the ADS case, it's not really compact. The radial direction goes off forever. That's the sinh squared radial scale factor that I've written here. Whereas in the de Sitter case, instead it's a sine squared, and the warp factor grows and then to a maximum that is finite and then shrinks again. So in the ADS system, slice D+1 sliced by de Sitter D, this is the picture in the Penrose diagram. We'll be interested in a finite patch of this, the infrared, a certain infrared patch up to a cutoff. And if you look at the metric, or equivalently the geometry as depicted in these Penrose diagrams, the infrared limit of ADS, DS, matches the infrared limits, there are two of them, of the DS-DS. So remember again, on this Penrose diagram, each point is a D-1 sphere. And if you start here, where it has gone to 0 size, and move out, this is a copy of this. And so on here as well. It's a second copy, the infrared part of ADS-DS. And again, you see that in this metric. If you look at either sine or sinh at low values of that warp factor 3, and the sine case, again, has two regions where the gravitational redshift factor is very strongly warped, giving us a low energy, infrared region in two places. Okay, so this is a very simple macroscopic statement, and it suggests that there is at least semi-holographic description in which we can dualize the infrared throats here into something that's similar to what you get from a CFT on de Sitter at energy. Okay. Now, microscopically, we landed on this again in a way that I hadn't anticipated originally. from thinking about this question of this very pedestrian approach to the cerulography, where we start from an ADS-CFT dual pair, one that we have in string theory, like the celebrated D1, D5 system, and we add ingredients to turn it into a de Sitter theory. So again, we did bother to do that in detail in a three-dimensional de Sitter paper I keep bringing up rather nostalgically at this meeting. But here we're going to take that as given and use the basic structure of it, basically the fact that it's metastable. So I want to explain this step by step. Let's start by reviewing the ADS brane construction, which in general is some branes probing the tip of a cone or probing the origin of flat space-time. So in this little cartoon, that's this picture. You have NC branes at the tip of the cone. And you can do the following thing. I'm going to belabor this construction in a sort of silly way on the ADS case and then see what happens to it when we go to DS. Okay, so the ADS brane construction is D branes probing the tip of the cone. Now the D branes eventually in the solution are traded for the flux terms, but the cone is related to this curvature term. So the base of the cone is a positively curved space. And the equation for a cone can be written in this analog cosmological way where there's a radial Hubble evolution. So the this change in the size squared, like the radial Hubble squared, is given by the curvature contribution, and the solution of this is a conical geometry. Okay, so that's ADS. Okay, in the same spirit, let's just ask, what do we get if we replace these ingredients with the minimal thing that could give de Sitter? Okay, so there we know that we've got to do this uplift. So instead of the positive curvature piece, we're going to have something for which the sign of that is flipped. The sign of the leading term needs to be flipped. The simplest thing to have in mind is something with, say, negative curvature, although there are different versions of this. And, well, so in this radial Friedmann equation, what happens? Well, the curvature term has a flipped sign. Then there's another term because there is this dip in the potential from, say, orientifold planes. And those, we know, come at subleading orders in 1 over r. Okay, so the basic structure on the right-hand side of this equation will be a Friedmann-like equation in the radial direction with a minus sign here and something subleading here. Well, what that gives you is a radial evolution which grows and then shrinks again. So you reproduce from this brane construction, from what happens to the brane construction of ADS-CFT when you uplift to de Sitter, and the way it works in string theory minimally is you predict these two infrared sectors from a completely different point of view. So this also predicts some kind of dual description involving two low-energy effective field theories, again, based on these basic features of the minimal kind of uplift that can exist in string. So that is something that motivates me to take this quite seriously. Now, a third way, so I said 2 + 1, and you might be wondering about DS-CFT, which is kind of the older sibling of DSDS. It's been much more studied in some ways, and I want to say a couple things about that. So first of all, for our purposes today, let me just explain why it gives a similar statement, so it's a neat thing. There you start from a conjecture that the wave function, the Wheeler-DeWitt wave function on a space-like slice, which is a functional of the metric on that d-dimensional slice, is given by some CFT partition function with that metric as source. But then if you want to calculate generic observables, like some expectation value, you're led to integrate psi dagger O psi. And well, mathematically, what is that? That's an path integral over the metric of two separate but isomorphic CFT partition function sectors with this operator. So once again, you get, for a rather different reason, a statement that you have two identical CFT sectors which are coupled to gravity. And it probably should be cut off in this case too, because we know that de Sitter decays, at least there's overwhelming evidence for that in string theory. I also want to emphasize that it's in the microscopic string theory context, it is not at all reasonable to simply take ADS solutions and continue them to DS. That gives you imaginary fluxes, and that's not the way it works. Anyway, so let's come back to the DS-DS correspondence, where the emergent direction is radial, and where we can easily study the properties of the state, which is the goal of today's talk. Okay, so just returning to the statement, there are two independent arguments plus the DS-CFT confirmation, let's say. This statement remains with some ambiguity, obviously. How are they cut off? What relevant operators are deforming the low-energy CFT? TT bar is one of them, because we have gravity, but we don't know the general statement of that. Nonetheless, we'll get quite far in studying the properties of the state. Okay, so I just think this agreement is unlikely to be a coincidence. And of course, we're somewhere in the middle between pure speculation and exact solutions, as with almost all theoretical physics. So, proceed. Okay, so I really want to get to the new stuff shortly, but in this series of papers we've had over the last decade or more on this topic, we've done a bunch of calculations, including transmission calculations between one warp throat to the other, which indicates interactions between the two. There's an interesting analysis one can do of the holographic RG following from Heemskirk-Polchinski, I think, maybe just Heemskirk-Polchinski. So you could ask the question, in ADS, you have a CFT. One way to think about that in a mechanical way is that you've stabilized the scalar field, so V prime, the moduli potential, is 0 at your solution. If it hadn't been true, then you would have had to let the scalar field evolve radially. That would be a non-CFT, it would be a RG flow. And so, that leads in the holographic RG to Wilsonian effective action in this version of exact RG in which single trace couplings don't flow. Well, in DS also, if you succeed, if you have this minimum, then V prime is also 0 there. So in the context of the holographic RG, it has the same level of constraints. It's not the same statement, but you actually also find that single trace couplings don't flow, and you find that multiple trace couplings are determined by the lower trace one. So there's a lot of work one can do on this duality. Let me, before getting finally to the simple calculations of the state, let me note the role of gravity here. So let's say work in the d plus 1 equals 3, d equals 2 context. Gravity could be formulated as Liouville gravity coupled to this matter sector. And the de Sitter evolution is something that actually was studied back in the day, developed much further by Martinek and all recently, where you have a matter sector such as the one we will have, with the two CFTs mixed in some way, and coupling that to Liouville, where the Liouville field is like the scale factor, you find that the negative ground state energy of the matter sector combined with the Liouville cosmological constant gives a Wheeler-DeWitt wave function that describes this global de Sitter, where the scale factor comes in and bounces out. And again, it's interesting that these days one can trade two-dimensional gravity, at least some versions of it, with the TT bar deformation. So perhaps one could get rid of the gravity entirely, depending on the outcome of those discussions. Okay, so I made a point that the de Sitter goes only up to a finite scale. What is that scale? We know what it is. It's a scale where the warp factor goes to 1. So when we consider this product of CFTs, we should only include a finite part of its Hilbert space. So we will simply crudely cut it off, taking very seriously the holographic RG at the radial scale corresponding to that warp factor. That gives a very definite count of states. It's the entropy of the black holes at the Hawking-Page transition, which have been derived in a more field theoretic way by Hartman, Stoica, Keller, and others in this dimensionality. And so you have a finite dimensional Hilbert space involved. Now you might guess that because I quickly explained that we had studied some interactions between the two sectors, that they are rather strongly coupled, and that as a result of that, the ground state, the long-lived state corresponding to de Sitter, might be highly mixed. if it's maximally mixed, then the density matrix of one of the sectors from tracing out the other would take this very simple form. And based on the strong interactions, you might guess that. If that were true, then we should find that the Rényi entropies agree with the von Neumann entropy, and they all boil down to log the dimension of this finite Hilbert space. And that is something that we can check holographically. So I'm building from the beautiful review talk that she gave, where these concepts were introduced. So first of all, the von Neumann entropy, the two sectors are just the two sides of this spatial sphere at tau equals 0. Extremal surface is anchored on the UV slice, is just very simply this sphere drawn in black here. The entropy of that is this geometrical quantity, or in 2 dimensions, c pi over 3. And it is the same thing as the Gibbon-Hawking entropy for this observer. But is it correct to say that we can count that by simply identifying it with the log of the dimension of the Hilbert space of each of our equivalent CFTs, and the cutoff in the way I explained? And for that, again, we need to calculate the Rényi entropes. So this is something that she explained in general. There's a version of the Rényi entropes given here that is directly related to a geometrical question in the bulk, which is the area of what she calls a cosmic brain on the Euclidean geometry, anchored on the UV slice, sourcing a deficit angle, this form, for the nth Rényi entropy. Now, happily, the reason I left this to the end of the talk is because it's really simple to calculate. The Euclidean geometry in our case is a sphere. So, like with Andy's joke, only a cosmologist would call a sphere Euclidean ds. It is. And here's the sphere in complex coordinates. Here's a projection of the sphere that gives the correct deficit angle. And the fixed locus of that projection is in these coordinates, d1 equals 0. So that leaves z2 squared equals LDS squared, which has the same area in Planck units as for all n, and including the von Neumann entropy. Okay, so at this large C level, the entanglement spectrum is flat. At the level we're calculating, large C, we do get the statement that all the entropies agree, and they're the log of the dimension of the Hilbert space of either one of the sectors. Okay, so let me comment on the interpretation of Gibbons-Hawking. What we're basically saying is that there is a dual holographic interpretation of the area of this RT surface as an entanglement entropy between these two matter sectors. And that's this SRT, which, again, is the entanglement entropy. Sorry, this is typo. I corrected the online version. And again, it's given by log of the dimension of Hilbert space. And it's also equal to the Gibbons-Hawking entropy for this observer, for whom this area is their horizon entropy. And that makes sense. This observer is somebody who's never going to feel the second side, and they must trace over. So in this sense, this holographic dual description of the entanglement entropy also gives an interpretation of the Gibbons-Hawking entropy. What about late times? Again, there's a tour de force analysis by Hubini, Raghunathan, and Takanagi, doing that in generality. In our situation, it's quite trivial. The extremal surface is at this UV slice, and it's a little more complicated at some non-trivial geodesic on that slice in the d plus 1 equals 3, d equals 2 case. Now, an interesting feature happens here is that if you separate the points delineating the entangling region too much, then just the formulas appear to give a complex solution. There's no real geodesic. That's what's happening is the geodesic is reaching the presumed future infinity, which of course doesn't exist in string theory anyway. But instead, we can just repeat those structures for each Hubble patch and get a certain entropy per Hubble patch. the volume law because we're integrating out half of the matter sectors, integrating out internal degrees of. We can go forward into the decay. One nice thing about the DSDS framework is that you can build in the decay to the runaway we call FRW perfectly well. You get a somewhat more complicated two-throated warped metric with some time dependence, but good hierarchies. And we found some interesting features of that in the past, that the entropy bound grows in a certain manner, as does the long mass. So gravity decouples asymptotically in this setup. The growth of the entropy bound that we found in the past agrees with the growth we find here of the RT entropy, or HRT entropy. Okay, so I think we're in good time. So one thing I just said but might repeat is that we're getting a volume law here, which of course makes sense because it's integrating out internal, tracing out internal degrees of freedom. There are some pre-existing examples like that. People studied entanglement in different momentum sectors or in internal, in the S5 directions of ADS CFT. In the basic observer patch, we're dealing with of order C degrees of freedom, so we're kind of inside the matrix in the sense of Susskind and Witten. It'd be nice to interpret the entropies we find in this FRW phase further, and I think we can build on this new understanding of the structure of the state in DSDS to do more, to, for example, look at the HKLL construction of local operators and calculate their correlation functions in this highly mixed state. And we hope to use more details of the dual description, for example, in the D1, D5 model, or maybe simpler toy models to analyze the interaction Hamiltonian, the coupling between the two CFTs, matter sectors, in more detail, and derive from that the structure of this mixed state, again, in more detail. So let me stop there. Ask for questions.
Great, thanks very much, Eva. So we're running a little behind, but we'll have time for maybe one or two quick questions. If there's questions in the audience. Oh, yeah, right over.
So, Eva,
Oh, hi.
So what is the consequence of the decoupling of gravity in late time in the entanglement entropy?
Yeah, two things happen. I said that quickly. The entropy bound and this total entropy that we get goes to infinity, and at the same time the lower dimensional Planck mass goes to infinity, meaning the gravity coupling goes to zero. So that means that at very late times, it could become a completely precise description with no residual gravity. But that's only an asymptotic statement at infinite time. But that is the statement, if that's what you're asking.
So if I understood correctly, you're sort of recasting the Gibbons-Hawking calculation of the entropy, but there wasn't any, shall we say, microstate counting here, like in the sense of, say in ADS3, you can use the Carty formula to reproduce.
Oh no, you can't.
Yeah, so can you comment on? Can you comment?
Yeah, let me. Sorry, I not make that clear. It's building from. Okay, so the key part of this is this cutoff for each. So what is the Hilbert space we're dealing with? It's this one up to the radial scale corresponding to this warp factor. That has a definite count of states from the ADS CFT. So we are assuming ADS CFT gives the right count of states, okay? But once we have that, we have the dimension of this Hilbert space. That combined with the Maxwell mixing of the state implies that the entanglement entropy is the dimension, log of the dimension of this Hilbert. So it's, if you believe that this is essentially a count in ADS CFT, and I think these 3D modular transformation analyses by Hartman and company went pretty far that way. They brought the Carty formula down to this transition. that's what's embedding into this story to give.
Okay, let's thank Eva again.
So again, we are moving the schedule 30 minutes earlier. So the afternoon session will start at 1:30.